Okay, good morning. I hope you had a nice evening. You're ready for the last long morning of presentations. Let me just say it was a pleasure to have you here in Coimbra for the past 3 days, and I'm looking forward to seeing you again in Portugal as soon as possible. We'll start with our fifth keynote speaker, Dr. Viviana Maggioni from George Mason University. The floor is yours.
And I can use just Okay. Good morning, everyone. Welcome to day 3. Let me start by thanking so much the technical committee and organizing committee for inviting me here to give you a keynote talk. Luca Brocca, here is the title. I know you have been asking me all week what I was going to talk about. Not only the title, but this picture was actually taken in Todi, Umbria, in central Italy, when I was visiting CNR a few years ago. What a great precipitation system there. We were at the spa, so we were safe. But I'm Viviana Maggioni, for those of you who don't know me. I'm currently at George Mason University, not too far from Washington, D.C., but moving back to this side of the pond in just a couple of weeks, and I will be joining the Politecnico di Milano. So I also want just to mention that the work I'm showing you today is just a collaboration with many of PhD students in my group, some postdocs, and even some high school students helped a little bit. So in case you haven't had your coffee intake of the day quite yet, I'm just going to start from the conclusions so that you can take a nap right afterwards. I was trying here to give more than a technical talk. You'll see some plots and maps. Don't worry, you're going to get that. But I also wanted to see if we can try to summarize what really matters when we talk, when we study precipitation trends, when we study precipitation extremes, and what can we do differently moving forward. So number one, for this, size matters. We have been talking about scales quite a bit in the past couple of days, so this will just bring things together, hopefully. So when we try to analyze precipitation and different types of precipitation, then we always need to think about scale. And when I talk about scale, it really means not just the temporal scale at which we do things, but also the resolution that we're dealing with, and possibly the latency as well of those products. So the second one is precipitation is a very generic term. So when we study precipitation, we also need to be a little bit careful about what we really want to study. Volume, frequencies, intensities, phase. Lisa, I'll talk about snow. They all may be changing in different ways. They may react very differently to the kind of technologies, the kind of methods that we're trying to apply here. And last but not least, different products may be telling different stories. Which one is best? It really depends. We have already mentioned this many times, which is great. But really, what to choose depends on what we need it for. So the first thing I'm going to be showing you is resolutions, moving from coarser scales to finer scales. And since it's an international precipitation conference, you'll see I'll start in the US, move to West Africa, and take you all the way to Southeast Asia. But the first part of the talk is really focused on the contiguous United States. This study was really driven by a colleague who is a climate scientist. And we were trying to ask ourselves, they study precipitation trends at way larger scales that we are used to. And we want to go down all the way to the 1 kilometer and try to find trends at the 1 kilometer scale. What does that really mean? Does it matter at what scale we do things? Clearly it does. So what you see here is a Climate Prediction Center Unified CONUS data set. We're going from 1948 all the way to 2022. And what we did was to start at their original resolution of 20 kilometers and went up, so went coarser. So we aggregated it to 50 kilometers, 100 kilometers, which is usually the scale at which we have climate data. And then, even at the regional scale, so we use the NCA, the National Climate Assessment, climate regions to look at trends at the regional scale. And then we did two different things. We aggregated using two different methods. One is the classical nearest neighbor interpolation, so whatever falls within your larger pixel gets aggregated. The other one is what we call a more conservative regrading, and I can tell you all the details about it if you're interested later, but it basically preserves mass. And once again, it's one of the mostly common used interpolation methods as well. And then what we did was to use Stilson slopes and Mann-Kendall tests to check trends at each grid point. And first thing you see is that here we are not looking at trends quite yet. We are just looking at precipitation. There's a snapshot there. And what you see is just the regrading itself gives you different results. So that's number one. When we talk about scales, we really need to be mindful of what we use to go from one scale to the next. So just not downscaling, which is already very complicated, but even when we upscale, which is supposed to be the easy way, it may not that be straightforward. And then we looked at total annual precipitation. So these are slopes, so it's Stilson slopes. So these are trends. Number one thing, does it really make sense to look at trends at the 28-kilometer grid? Do we really believe that we have a very dark pixel and next to it one that almost has no trend? Going back to Effie's presentation the very first day, we need to make sense of this kind of variability, which is probably not quite real. But then again, once we aggregate up to a larger scale, then we start to think that maybe that makes a little bit more sense. Once again, we have possibly different trends if we aggregate in different ways. Even at the regional scale, if you look at the bottom two plots, you see how in one case, to the right, you have and that's a significant, I'm not showing the Mann-Kendall test, but that's a significant decrease in trend, whereas to the left, for your nearest interpolation method, you almost see no trend. So once again, be mindful. Things get even more interesting when you move from total volumes to other characteristics of precipitation, like extremes. So this is the daily maximum precipitation, and once again, slopes. Very similar story here. Sometimes it gets, that's the same plot, sorry. Thank you. This is the wrong plot, apologies. But once again, very different. If we aggregate at different scales, we may get a different story. And it doesn't show here, but the conservative regrading method is also quite different. So I think this is all the, so we go to the moon, but converting Mac to Windows is still a problem. Fine, we'll deal with it. Because it doesn't show the animation, fine. But, and when we look at significance, once again, that also quite changes. So it's not just the amount of change in precipitation, but it's also how significant that trend is. So if I want to summarize very briefly, what we are seeing here is clearly, significant trends may be overlooked once we go to very coarse scales, like the regional scale, but maybe that's what we want, right? That's the information that we need. The other problem is that all these processes are highly nonlinear. So trying to predict what we may see at the next level scale, it's almost impossible. And just last but not least, the methods we use to regrade our data sets also play an important role. Gonna move to West Africa, where we had a project that was funded by the Servier program, RIP Servier, that's gone. But the goal of the project was really to develop a flash flood forecasting system for West Africa. And our group in particular was in charge of studying how extremes are changing in the region, and specifically the extreme precipitation that triggers those events. So the first thing we did was to collect data about the flood events. So here you see a list of flood events in Ghana specifically that were recorded, and then we looked at precipitation. Here the precipitation numbers that you see are from iMerge final run. The red box that you see there are precipitation values that exceeded the 99th percentile for the rainy days. So the first thing that you see is that some of those events, of those flood events, are associated with very large precipitation, expected. The orange ones are the ones that are associated with precipitation in between the 95th and the 99th percentile, also large rainfall. But for floods, not just the amount of precipitation that happens the day before is important, but also the cumulative in the previous X days. So we played a little bit with that, and the blue boxes that you see there are events during which the consecutive rainy days within the 10 days prior to the event itself exceeded the 95th percentile. And then there is one case in white with a star there. That event has a near extreme precipitation, about the 99th percentile value, but that occurred 5 days before the event. So we believe that it's possible that event was just recorded too late. And that's possible when you deal with data that are recorded with flood events that are just recorded by someone. So that's something that it's possible. We'll never know what's true. But then again, flash floods is what we were interested in here. So here you see a bunch of flash floods events across West Africa in the past few years. And what you notice here is that all of these events are clearly associated with very large precipitation events, as expected. Flash floods are fast associated with a lot of rainfall within a few hours, if not less. So how can we study? How can we hopefully predict these events a little bit better? Well, satellite data can kind of help, but clearly now latency is key. We cannot really use iMerge final that comes available just a few months after the fact, right? Although it's maybe the best accuracy product that we can think of. But we need to step back a little bit here and look at those products that are available quickly. And perhaps not quickly enough sometimes, right? So here you see iMerge early, available 4 hours after the fact. iMerge IR only, infrared only, also available 4 hours after observation. At the bottom, you have the GS map, the Japanese version of the product, near real time and now. So the near real time, also 4 hours after fact, but the now is available less than an hour, usually about 30 minutes. And then top right is PDR now, and that's from the Persian family, also available in between 15 and 16 minutes from observation. Slightly different resolution. Persian is available at 4 kilometers, the other at 10. Good thing that in Ghana we have 48 stations, rain gauges, that are managed by the Ghana Meteorological Center. And these events specifically was one of the ones I showed you earlier. It is a flood that happened in Accra, which is in the southeast of Ghana along the coast. So right away you see how iMerge IR only doesn't really pick it up, whereas GSMAP near real time, for example, shows that event quite nicely. So Here are the classics that we always look at, correlations and biases. Obviously, we use those gauges. This is only 3 years, so that's where we had high-quality gauges, and all the products that I just showed you. So very briefly, and we don't want to talk too much about the statistics, but the idea here is that if you have a look, clearly the ones that are available slightly later and the ones that include some passive microwave are better. Higher correlation and lower biases. The magenta line there is PDR now, and PDR is the one that only has the infrared in it, and it's also available pretty quickly. So a couple of things, you see a drop for all of them in about July. That's probably due to warm clouds that are really not picked up very well by our infrared. You also see an increase in bias in November. That's the second rainy season. It's a minor rainy season in West Africa, and that's when it happens kind of the opposite. So you have these cold clouds that may not be precipitating. So those two strange effects may be due to just the precipitation processes that these kind of products are really not able to catch. So, and then these are aggregated statistics. You really want to see if there is any spatial distribution that we should take care of. Maybe a couple of things. You see smaller correlations along the coast. Can be due to the product itself. It can be due to the gauges themselves. Again, it's hard to tell. And once you look at the biases, then the one that really pops up is the PDR now that shows the largest positive biases. So the blues here are positive, the red are negative biases. And an overestimation of rainfall. When we deal with extreme events and floods specifically, we really need to be careful about detection. There are two things that we want to avoid. We want to avoid having people leave their homes if nothing is happening, although that may be the safe way, but think about it. If I receive a warning, I leave my home, nothing happens. Fine. Second time, I may do it again. The third time, I may stay home. And that may be the time that is going to be detrimental. So we need to be careful with those false alarms and try to reduce them as much as we can if we want to make sure that we have an effective warning system out there. Opposite is also true, right? We want to avoid having people stay home if the flood is coming, if the storm is coming. So these two plots are showing you probability of detection at the top, false alarm rates at the bottom. And what you kind of see is that the iMerge family, which is the blue, has the largest probability of detection, so it misses a fewer amount of events, and decent false alarms, so it's in between the other two lines. So bottom line is probably that iMerge, in terms of detection, is the one that gives us the most consistent results. Now, what if we didn't have gauges, which is very common in West Africa? So I think someone yesterday, maybe Luca, mentioned triple collocation analysis. So that's very typical when we want to compare 3 different products and we really don't know where the true is. So 2 different models were used here, a multiplicative and additive. Usually the multiplicative is considered to be more accurate for precipitation products. 2 reasons: better predictive skills, and it can also disentangle the random error from the systematic error. However, if it doesn't rain and you multiply that 0 by anything, guess what? You're going to get no rain anyway. So that's why an additive model sometimes, especially in dry regions where you have a lot of zeros, may be something to consider. So here you see basically the best of the 3 products, and we picked 1 product from each family. So you have an iMerge, you have a GS map, and you have the PDR. So what you see here is that overall, iMerge is probably best for both, according to both models, in terms of correlation coefficients. And in terms of error standard deviations, things are slightly different for the additive model, where the PDR now kicks in, and sometimes the GS map too. Once again, do we really believe that in this cell we should use the GS map, and in the next cell we should use iMerge? Probably not, right? So whenever we look at this map, we should always try to think what they mean, right? To me, the outcome here is, if I had to pick one, I would probably pick iMerge. But remember, iMerge is only available 4 hours after the fact. So if I want something faster, I may have to go to different products. How am I doing? The nice thing is now we can expand this to West Africa, not just Ghana. And what we get is something similar. Overall, we get a lot of blues, which means that iMerge is probably best. But this is really just to tell you that there are options for us to try to compare these products and, again, try to get some information out of it. The last thing I'm going to show you is a study in the upper Mekong River Basin. Probably know that this is a very large river basin that supports the life of about 70 million people, and it's across 6 countries. Not only that, but I recently learned that it's one of the most biodiverse river systems in the world. It's second only to the Amazon River Basin. But we focus only on the upper Mekong, which is also known in China as the Lancang, and it originates in the Tibetan Plateau, and it contributes to about 45% of the entire basin's river flow. So again, quite important within that river basin system. China also has a cascade of mega dams in that upper Mekong River Basin, and controls the downstream flow, which gives it a lot of geopolitical power. So once again, it's extremely important. And downstreams, you have countries like Myanmar, Laos, Thailand, Cambodia, and Vietnam. So once again, it's one of those regions in the world that's not just important hydrologically speaking, but for many other reasons. And here we're introducing a couple of extra complexities. We are introducing reanalysis data, not just satellite-based products. We have complex terrain. We don't only have rainfall like we had in West Africa. We have snowfall as well. And clearly, it's complex terrain. So we looked at 3 different reanalysis products, ERA5, MERA2, which are well known, and the Japanese reanalysis, which has a resolution that is somewhere in between ERA5 and MERA2. It's about 0.56 degrees. And then we have iMerge final just for comparisons. So just a couple of notes here. This was done in collaboration with University in Tokyo, visiting student Kansei Fujimoto, who spent a month at Mason with us. And this is, actually, he was supposed to present here at this conference, but for some reason his talk didn't go through, or his abstract. So presenting on his behalf, which is great. So here you see total precipitation, and then we also plotted rainfall and snowfall for all those 4 products. A couple of things to note. When it comes to total precipitation, you see that the 3 reanalysis products, and these are averages, yearly averages for about more than 25 years time series. The reanalysis data sets all agree, whereas iMerge, which is the red line, is a little below those. What is real, what is true, we really don't know at this point, right? We're just trying to make like a relative comparison. But the interesting part maybe is the snowfall, since we haven't talked too much about it today. So when it comes to snowfall, then JRA, the Japanese reanalysis, and iMerge are the closest. And that's kind of interesting. It seems that they agree with each other much better than the other 2 reanalyses. And the very last thing I'm going to show you is expected snowfall. So this is, again, for the same period, 1998 to 2024. And for each wet bulb temperature, which is what you see on the y-axis, and each elevation, we are going to look at the expected amount of snowfall. So I think that the interesting thing here is that when you look at the three reanalysis data, they look very different. And even the color bars here are different. So it also means that we need to be careful when we want to analyze precipitation and different phases of precipitation, even using just the reanalysis data sets. So once again, I'm not going to repeat myself, but hopefully I convinced you that there are different things that we should consider and just be careful when we analyze precipitation. And maybe the bottom line is it's all good as long as we justify what we do and as long as it makes sense for the application that we have in mind. So with that, muito obrigada, and thanks to my colleagues who helped me deliver this presentation. Happy to take any questions.
Any questions?
Thank you for the talk, very nice. That's quite problematic talk, I think. Because, for instance, if you don't have any experience on which precipitation product to use, you just use one of them. Even the analysis, they tell different stories. And of course, in several analyses we did, it's particularly if you go in Africa, if you go to extremes. So what should we do?
What should we do? We should be here. I feel like maybe that's one more reason for us as a community to come together and keep studying what we're studying. So I feel like that's the bottom line of this talk should be, let's keep working together. Let's keep answering questions that are hard. We talked about uncertainty a lot, and we have been talking about uncertainty even before I was interested in studying hydrology. So, and we still don't have an answer. We don't have the set of metrics yet. But maybe if we sit down together, we can come up with some answers. And again, I'm not saying that it's all bad. It's true. You're right. You're very right. We need to be careful. If you come and you're just picking the first product out of the blue, that's probably not going to be the best one. If we offer some quality control, some green, yellow, red flags, that may also help to just guide the users in the right direction.
Just to reply, probably something that we can expect from the application viewpoint, and for instance other communities are doing something like this, is to provide guidelines or to provide kind of open system for checking the data. Something like, I don't know, you can put all the products available and you can have a first look to the quality of the data.
Yes.
That is tested by people like you that have the experience on these products.
Thanks, Luca. Yep, I agree.
I was wondering about your thoughts about order of operations when it comes to regrading and interpolation methods. So, like for reflectivity, you have some choices as to whether you interpolate or regrade in linear space or log space, and it makes a difference. And there's also choices you have to make in terms of how do you do things like inverse distance weighting and how that changes results. So do you have a sort of thoughts on the order of operations when you do regridding for all these different products?
That's a tough one. I don't. Also because you have almost infinite options, right? When it comes to aggregating, disaggregating. I feel like, once again, if we can offer some support when it comes to, in this case, this is probably the best. In that case, you just need to be careful, right? If we can add that kind of information, that kind of flag, I feel like it it can help, at least. It doesn't solve the problem, but it can help.
Do you have any no-nos, things that you don't want people to do when it comes to regrading?
Yeah, I do. So number one, going back to the pixel to pixel, right? I don't want my student to say, oh, this pixel has an increasing trend that is super strong, and next door, 25 kilometers away, I have no trend. That kind of information, that kind of interpretation is wrong.
Thank you.
Right? Of course.
Thanks, Viviana, for that great talk. I guess I would just, I don't think this was available probably when you were looking at Ghana at the rainfall, but Rain Over Africa is a pretty great new product. It's based on UNet, convolutional neural net kind of stuff that should be added to the list.
Fantastic, yes,
yeah,
absolutely. No, probably was not, because this is a little old now. It was the previous surveyor, so we're talking about 5 years ago at least. We had a lot of ideas for the new surveyor. It didn't happen. But again, I'm moving to Europe, hopefully more flexibility on using the data sets I want and keep going. So I would love to have a look at that. Thank you, Chris.
So yeah, Viviana, I'm so happy to see here 2 applications that have exactly this problem. I have a positive trend here, but next pixel I don't, or I have a negative one because I was obsessed with that. Yeah. And I regret not presenting much more about the method, because I should not average my signal and then see what happens. I should do my regression, whatever it is, at the resolution that I have the data, and then ask my coefficient, say linear regression or whatever represented there, is an estimate, just only an estimate. What is the best way to use the information and the coherence of the signal and of the noise? And that's not trivial. But we go into a spectral linear system theory. I put in my estimate, I get out my true, okay, will be the spectrum of the true, meaning the map of the coefficients, okay, divided by the spectrum of the estimate. Now, there is a trick. How do I know the spectrum of the true? But you can, through perturbation, imagine that you perturb the years. And then, that will be the regression that you would find will be like the error signal and so forth. So there is a formal way, and we should make sure that we get, the paper will be out soon, and get this information out, because it's not right to average the signal this way or that way, etc. Use all the information, but then take advantage of the special signal that is there that cannot flip from one pixel to another. And it's very interesting, if I presented it, that the support of the filter that comes out, which is a low-pass filter, tells you also, and we have a map, what is the optimal averaging, which is weighted average, 30 kilometers or 100 kilometers. It depends where you are. So,
exactly. Yeah, I completely agree, Effie. And this was done towards that direction, okay? It was not trying to solve the problem. It was trying to show how things are currently done and why they are not working. So I know that you have ways of solving the problem, and I think, this is kind of a justification for coming up with new methods that make more sense, that can use a spatial structure of rainfall and precipitation in general.
One last question.
Is it okay?
Jessica?
Thank you. Nice talk. It was really nice to see some of the international components. And that's something, so a lot of the talks that we have heard and stuff have focused on the US or global scale things. And it's really nice to see this about Africa, and really it kind of points out that we really need more evaluation, and we need, like for me, we've done a study in Africa, and gauges, we could only get our hands on a few gauges for a long time period, and just the information's just not there. And so it's really nice to kind of see it, highlight it too, to say like, yes, there's the issues of our methodology that we need to deal with, but then also like so very, very nice. Thank you.
Thank you, Jessica. And I know that you're interested in landslides, and that's even another order of complication in a way, right? Because you basically need a threshold. It's happening, it's not happening, right? But if that threshold is wrong, then you will never get the right result, right? So, something that, again, we need to think about and hopefully this community can solve. Thanks again. Thanks for the opportunity.
Thank you. Okay, so next we have our second panel. Today's panel is moderated by Carolina Sá from the Portuguese Space Agency, and I'd like to welcome the speakers for this panel to join Carolina on the stage. So we have Bruno Carvalho representing WeatherStream, Burke Riggs from Washburn School of Law, Pierre Kierstetter, Noah University of Oklahoma, and Alfred Dias, Vice Rector of the University of Coimbra.
Okay. So I think, good morning, everyone. Good morning, everyone. So I would like to thank Vasco for the invitation, for setting up the panel and preparing it a bit. I think this panel is quite nice after the discussion we just had on uncertainties and how we move from data to decision. So I would just start by asking all the panelists just to introduce yourselves and tell us where do you see yourself and your institution in this value chain from data to decision. So are you a data provider, added value server, are you a decision maker? Or can you bring the perspective of a decision maker? So maybe we can start here from Pierre.
All right, good morning. So Pierre Kierstetter from the University of Oklahoma and with also the NOAA National Severe Storms Lab. I would say I am a data provider from the ground-based data, and I have an interest in hydrometeorologic impacts on the science side, with also a pet peeve on how to communicate the added information we extract from geophysics into decision-making.
I'm Burke Riggs. I am not a scientist. That's the safest thing you'll hear all week. I'm a law professor and an historian. My focus is on water law, and what draws me to this is as a translator, an exploiter perhaps, being able to harvest the science here to think about how it can be used to better understand water use allocation agreements, and also how to understand property rights in the use of water in a more dynamic and accurate way.
Hello, good morning. My name is Alfredo Dias, and I'm civil engineer, so I don't really have a huge or significant contact with this area, but while I was a student, I had some in hydrology, for instance, but I have some by other reasons. I have some contact to the territory in our region, in Central Region, which indeed is very much impacted by all these phenomena, and so I will try to give a view on the society, on the communities, and how we can make a way to help them living with these situations.
Good morning. Thank you, Vasco. Thank you, Carolina, for the invitation. Thank you to the conference. My name is Bruno Carvalho. I'm representing WeatherStream. My background is in basically space. We are data providers. We're deploying microwave sounders as we speak. We launched our second generation satellite last March. We're starting to get the first data sets, calibrated data sets down. And I think we're going to go through some of that in terms of what it means to have near real-time data and nowcasting, and trying to see if we can bridge the gap that Vivian showed in the previous slides. And it's really about the data sets that we're trying to bring down, which are, we believe, unique at the moment in terms of what we are providing. So while I'm sitting in the data provision side, as a consultant, I also touch on other little areas in terms of the data usage, in terms of going towards the decision making. I'm not a decision maker myself, but what we're trying to do is to make the data available, not just the data, but the information, actionable information that people can use to make decisions, because the data just for the sake of data is no use. We have to really process it and make sure that people are able to make sense of it.
Okay, thank you. So we have a quite diverse panel, and I think we touch all the value chain. I would ask Vasco to keep an eye on the clock because I forgot my phone there. So thank you. So let's start with the gaps. So we are going from data to decision. Where do you see the gaps today in terms of science, in terms of communication, of institutional or political process itself? So maybe each of you could give an idea of what, from your area, your perspective, what could be the gaps, or where do you see the gaps?
Okay, so you will probably need to shut me up at some point. I think we have a number of gaps in terms of communicating our information when we estimate precipitation. We have spent a lot of time over the last couple of decades nailing down the average amount of precipitation, but we don't provide the entire information. And that is probably a fundamental mistake when it comes to making these products suitable for actions. Uncertainties have been discussed a lot. I don't think uncertainties tell it's better than the mean, but what we need actually is the entire distribution of possible scenarios. And I have seen that people are not interested in single quantitative values. They are interested in their situation and their event of interest. So it's a matter of synergizing the need of the end user, making ourselves relevant. I think that's what Chris has been highlighting over and over again over the last 10 years. We are not getting money if we are not relevant. And at this time, I will give you an example. I don't think anybody in this room is able to tell what the economic value of iMerge or economic value of GSMAP. On a different, there is a kind of a sister community of ours, not satellite, ground-based radars in the US. They are renewing their radar network because it is aging. Like in 10 years, there will be no way to maintain the radars that they are. And they had to, so these communities, the National Weather Service, had to demonstrate why it is worth it to renew the radar network. And they performed an analysis, asked a company called MITRE to evaluate its economic value, and they came up with a number. The number is about 9 billion per year. That's the economic value of for aircraft, for protecting people from tornadoes and floods, and so on and so on. So imagine what is the economic value of iMerge and how we can sell that to make ourselves relevant to agencies. We don't know this information, so we are starting from very, very, very far. Next, so we need, I think Jessica highlighted it pretty well yesterday in a colorful manner. Well, we suck at it. We suck at making ourselves relevant. So I think there is a major gap here and major effort we need to make. I am in my the last thing I will say. I have more points, but Vasco is probably going to shut me up. Or Lisa, where is Lisa Milani? Yeah, okay. She's used to that. In the previous discussion panel, a gentleman talked about parameterized insurance. And I found that it's a new practice. I'm not very familiar with it, but I Googled it a bit, and it seems to me that it is very adapted to what we can do. Because let's say we are making an effort, and instead of retrieving simply a mean value, we retrieve the whole distribution, and we provide that to users. The user, let's say an insurance, agrees with a client, here is my precipitation threshold above which you will get reimbursed. That's parameterized insurance. And we can use that bridge much more tightly our precipitation products with applications with insurance. So I think there is progress being made there, and but we need to work on our own relevance. So I will pause here.
At a more general level, I think I would say that the gaps, as I see them, are mostly in the area of communication as well. Across the American West, there is a hostility among landowners to actually report data of their own water use, because there's a suspicion that the government will somehow use that data against their own interests. And what we found in states as diverse as Colorado and Idaho and California, that once farmers who use over 90% of the water in the American West start to make decent records of their water use, they fear the government less and understand their property rights more. And that allows them to think about conservation choices in a way that perhaps they hadn't thought about before. And I'm always struck by this, because these are extremely sophisticated businessmen who hedge and borrow and grow varieties of crops. And yet there is a cultural obstacle in terms of using really simple data for their own benefits. So I think communicating this data overcomes cultural obstacles in a remarkably short amount of time. At the agency level, obviously, the more data an agency has to back up a particular decision, even a politically problematic decision, the data can help them through the administrative law process of defending those decisions. For example, the United States Fish and Wildlife Service, under the previous administration, or the Biden administration, decided to assert federal water rights to the Okefenokee National Wildlife Refuge, which is home to endangered manatees, because it had the science behind it to show how a nearby mine could affect water quality into that wetland. And finally, at the political process, data allows the effective deployment of shame. And I think the most spectacular version of this is in the Central Valley of California, which since the 2000s has suffered a terrible drought. Groundwater depletions in the Central Valley are extreme, and it wasn't until the land subsidence caused by groundwater overpumping had started to buckle surface water canals that irrigators in the Central Valley knew they had to do something. And within 2 years of this happening, with the USGS and other really big players in California like UC Davis and other schools, they were able to get legislation through the California legislature, the Sustainable Groundwater Management Act, that has done more in the last 10 years for California groundwater than the previous 100. So never underestimate the power of shame in using your objective data sets.
Well, I fully agree with the people the colleagues that have talked before. I think that communication is the key. And I'm not from this area, but I am also a researcher, scientist. So I think that is absolutely critical that we explain science in a simple way that communities can understand it, and that we explain the practical impact of the phenomenon and why they happen, what they are not. Because people will never follow something that they don't believe. They first need to understand it, then they believe it, and then they follow what we tell them. And this is particularly important in a time like we are living, when the scientific knowledge is sometimes under press, even we can say it under attack. So in some communities with old people like we have here in our center region, that can go relatively easy on them. So they create parallel realities, and then it's very difficult. Doesn't matter the quality, the accuracy of the data, because it won't work. So I think that it's a big job for the researchers and scientists to create a trust relationship with the communities, that they understand and they believe on what we say. Because, of course, in the end of the day, we know that there are always uncertainties, namely in this area. So sometimes they will say, oh, there was a red alert, oh, it was not that bad, or it was an orange alert, it was much worse than what they say. That can happen, and we know that can happen. They need to understand that that can happen, why that happens, and that doesn't mean that someone was not giving the good data to them, the good information to them. So this trust relation is very important. And of course, from my experience, I think that then we have to provide these through tools that they can use. And of course, someone with 70 years old, 80 years old, will receive the information in some ways. People with 20 years old will receive it with other tools. That's how it works. So we have, from my view, we have to provide tools that they use in daily apps, whatever, for younger people, news, talks for older people, whatever, that they are useful every day, and on which we are able to transmit the data and transmit the information that can be absorbed and then, in the end of the day, be useful for the communities.
Maybe just we have a few points here: the economic value, cultural obstacles, communication, trust, and we hear a lot about uncertainties. And we heard from the audience some guidelines. So how can we really communicate uncertainty in this area, and build it an information where decision maker can do a choice? Because should you communicate uncertainty, what is the amount of uncertainty that you should communicate? Because at some point, decision maker will need something that he trusts to make a decision. So what should be the strategy? I don't know, how are you working with uncertainty, but maybe you can...
This is a good segue in terms of what's missing, because I think the part of the gaps that we see in the market is obviously the data sets that we're bringing to the market, and otherwise we will not be investing in trying to bring those data sets down. But it's also the correlation effect. So what do I do with this data set that is new? How do I calibrate it? How do I reduce uncertainty? But more importantly, how do I correlate the data set that I'm seeing with the data sets that exist? And I think that, and this is not necessarily precipitation, this is other data sets, can be visual, can be optical, can be SAR, can be, we'll talk about landslides before. So there's a lot of information out there that needs to be managed in a way that we can make sense out of it. And this for me, it makes reduces uncertainty in the first place, in the sense that I have a data set that I can compare. On the previous talk, we had uncertainty linked to different data sets, different sensors, and you can see that the way you interpret those is depending on also on what you want to extract from that data. But more importantly, in terms of how you communicate that uncertainty, I think it depends a lot on context and to whom you are communicating that uncertainty. So if I'm communicating uncertainty to the public in general, I think maybe I don't want to communicate uncertainty in that terms. I want to be more assertive in terms of how I communicate that information so that an Amber Alert or a Red Alert is effective, taken seriously. If I am communicating to political decision makers and policy makers, then yes, uncertainty needs to be there. It needs to be clear what it means in terms of the risk that they are prepared to take. I'm not an expert in terms of how that is handled or needs to be handled. What I see in terms of every discussion I've been having with potential consumers and customers, including from parametric insurance, and we have a few stories regarding insurance that we can share. Because it's not just about trying to predict the future and trying to assess what the impact of that issue is, be it floods or droughts or anything that has to do with, particularly for agriculture, is very important. But it's also things like forensic analysis in terms of making sure that that event really happened, and then that claim that insurance claim is valid, and it's because there's a lot of fraud in insurance, in particular in some countries that we've been working with. So that also links to uncertainty in terms of I mean, there was a discussion before about one pixel here is a lot of rain, and the other pixel there doesn't. So how do you manage that as well? And it's not so much about uncertainty per se, but it's also how you interpret the data and how you make sure that what you see is actually what happened.
Thank you. So to answer or to try to focus on your question and build on what you just said, I think I have the feeling that we as a community has a very top-down approach. We are not getting inputs from stakeholders and end users very often, if any. So we don't have a tendency to really tailor our information toward making it really, well, useful for users. And I agree. Well, first off, we have difficulties in defining uncertainty. And that's already is a diagnostic issue here. As a community, we don't handle it well. Second, we have, over the last 10 years, I have seen discussions talking about uncertainty and how to communicate it to users. And these discussions don't really make progress. I believe this is because we have difficulties figuring out what is the interest of the user. And we might have it completely backward. I said top-down, we should probably consider an alternative approach, which is bottom-up, starting from, and is it our job? That's an open question. I think there is a market here for the private sector. Because that could be their job to take the information content that is coming from science and engineering and then tailor it to each specific situation. We don't have time for that, and this is not our job. However, we can extract, as engineers and scientists, we can figure out what are the fundamentals that every of these applications need. We need the mean value, we need uncertainty, we need extremes. So we can focus on that. There is another thing that also I'm not very familiar with, but this is about uncertainty. And because we are talking about what the future of this community and what the economic value of our scientific community versus the private sector versus agencies and politicians. So uncertainty is can be dangerous for us if we don't communicate it well. It can be used as ammunition, political ammunition, for people to say, hey, those guys don't know what they are doing. Let's focus on something else that is more actionable. So I'm not a specialist there, but there is definitely some, if we wanted to talk about uncertainty as a scientific community, I think we need to embrace it and be able to counteract these kind of narratives.
Okay. I don't know how we are with time. We were okay. I'm thinking, and I was remembering the event that we had, the Christine storm in Coimbra, and how the municipality was communicating to people their decisions. And it was, if this happens, we will do this. If this happens, was a bit more with the scenarization that you were mentioning, and that I find it quite an interesting approach to work on scenarios when communicating to the community. Okay, so let's go into maybe the cooperation. So climate and precipitation have no borders. How do you see people working together? But I was thinking in international collaboration, but also, as you mentioned, scientists and private sector, scientists and decision makers. Do we really need, is this bottom-up approach not really working well? And is that the agency's job to do that? Also, the space agencies and the international agencies. So what is your take on the cooperation? How can we work better, or what this international cooperation can bring to solve these issues on the data to decision?
I can start and I'll pass the microphone along. I think you touched on an important point, the bottom-up versus the top-down approach. We deliberately, and I think it was discussed on the panel yesterday, we're making the data available for free for two reasons. For free, particularly for research. Obviously, if you start generating money out of it, we want a bit of a royalty. But the thing is that for research in particular, because, well, two things. One is that we don't see this, our data sets are going to solve every problem, so we need to, again, to correlate that with information from the ground. More importantly, to ask the customer or ask the client or ask the stakeholders what they need in terms of information, in terms of actionable information. And this can be just the amount of precipitation, this can be the type of clouds, this can be the type of snow, you know, all temperatures and things like that. So trends, other parameters that we can extract from that information. But more importantly is to try to see what are the needs on the ground. I mean, you are aware we're involved in a few projects that are linked to either forest management, water management, that has to do with information that can flow into these data systems and into decision making. And I think that's important. I think both strategies are complementary, so the bottom up and the top down. Hopefully they'll converge. And that's what we were aiming for. But,
well, from my view, from the community point of view, I think that there is, of course, a big room for collaboration, because when we go to the basics, we don't have borders. The laws of physics are the same everywhere, and even the human being is quite the same everywhere, especially in emergency situations where we tend to follow our instincts more than sometimes our rationality. So I think there is a lot of room for sharing experiences and to collaborate, because we know that nowadays that the societies tend to be very fractured, but even so, I think that we can, at least most of all of us, agree that this is a win-win game, that the collaboration will give value, will bring value to each of the parts. Furthermore, in communities, and again, referring to the community I know better here in our region, I do think that simply sharing of examples, the good examples, what other people did, what went well, what saved lives, what saved the properties and the economic values from people, that will be very important, and doesn't matter if it is in Portugal, in Spain, in China, in America, in Australia, because somehow people will feel a link to those situations. And of course, we in Portugal tend many times to try to do everything from the scratch, which is not a good thing, special for a small country like we are. And we are not able to be successful with that strategy. Fortunately, we are in Europe, in European community, so that helps us a lot. But having said that, I do think that in many cases we just have to apply the good things that have been developed, that have been tested in other places, and of course share our own experiences. And in what regards to extreme events, I believe Portugal is in many cases a good example, in most of cases not by the good reasons, but life is what it is, and we have to live with it and use it the best way we can.
Well, the United States is the greatest country in the world because we've made more mistakes than any other country in the world. And I mean, I could not agree more on this. In terms of the value of comparative studies of various, water use issues. The Murray-Darling Basin in Australia, and the droughts and all of the concerns in there has been studied thoroughly in the United States. And, getting back to Pierre's point about it's not your job to be both a top-rate scientist and, the science whisperer for the greater community. That's just, you don't have that capacity. So I think developing positions or areas where there are advocates for what you're doing who have the time and the talents to communicate those things. One of the best things I've been a part of is the United States Department of Interior's International Technical Assistance Program, or ITAP, where USGS modelers are assisting far less funded, far under-resourced modelers in Northwest Argentina, part of the Lithium Triangle, to deal with issues of water use and water consumption in the lithium salars. And so by increasing capacity, you are building trust that then allows more efficient transmission of recommendations and governance ideas across legal regimes. So it's easier, say, to communicate an American idea in the United States to Argentina. They're both federal republics. There are ways to do this that are simpler than perhaps Bolivia, to take another example from the Lithium Triangle. But, my final point on this would be, we have old transboundary agreements that have certain assumptions. The Albufeira Convention on the rivers between Spain and Portugal, the Colorado River Compact, which I'll talk about later today. Then we have newer ones, on the Mekong River, which is quite worrisome to anybody downstream of China, and the Nile. Science can, I think, improve the governance of these transboundary regimes by updating the assumptions upon which the regimes were originally founded. That is a hard job, but the stronger the science is, I think the more reasonable the possibility is of reforming those agreements.
Do you still want to add something now? Or? Yeah, of course.
Unless Lisa is against it. Okay, well, I will do short. Okay. Sorry. Okay, so, well, thank you very much. I truly agree. I just have maybe a couple of other points. I think none of us, or very few of us, are working with policymakers. And I think this is a bit at the foundation of what you were saying. So improving the connection there is probably critical. Something we probably wanted to reconsider and stop doing is putting priority on basic research without thinking of the application. Ignoring uncertainty in communication. We present our products as absolute, but we have a lot of these different products that are each of them are absolute. It's not sustainable in terms of communicating what we are doing. We are shooting ourselves in the foot. Citizen science might be another way to connect with people. So I wanted to, my last point here is will be more connected to this community here, the IPC community. We started doing these regional or career level centered pre-conference workshops. I believe that it provides unique perspectives on regional challenges, approaches, cultures in doing science and communicating it to stakeholders. I think we have an opportunity to build on this in order to make ourselves more relevant as a community by reaching out to regional leaders who would organize this. So this year we have Daniel in the room who organized one in Europe. We have Shruti Upadhyaya who organized one in India, and that was Asia. And we had two others, right? I think reaching out to communities is something. We have this card to play. I think there is huge potential here and upside in order to make ourselves more culturally relevant somehow, and develop that culture of communicating what we are doing.
Thank you very much. Maybe we have time for a few questions from the audience. I don't know if someone wants to comment, make any question directly to the panel. We're good? Yeah.
Thank you. It's a question and a comment. So I think if we're talking about communicating with decision makers and other non-science players, then maybe we should start bringing them to the conferences as well, because we have really good experts, people doing a lot of great research on how to communicate. So how can we make this type of events more appealing to those communities, because they can help us do that translation. And the second comment, so when we're talking to municipalities or other organizations, quite often we see in workshops we organize this sort of confirmation bias. So we tell them, hey, this is a great product, this is going to solve your problems, and they tend to agree because they feel that pressure to, they're in this setting where everything is leading to that. So how can we try to reduce that and make them feel comfortable to actually say what they feel?
I have the mic in my hand. I'm going to quickly jump into this one because we are working with municipalities, and the Portuguese Space Agency has been doing a great work, and Caroline trying to promote Earth observation data from satellites to be used by municipalities, and we have a few projects running. And I think there's two elements that I immediately jump to when we first start talking to them, is they'll ask how much it's going to cost. That's the first thing, and they don't have the money to do it. And if they don't have the money to do it, it doesn't matter if you're pitching whatever you want to pitch, they don't have the money to do it. And even when we say, no, we're going to do this, we're going to make it available, it's going to be free, they're still going to ask how much it's going to cost me, because they still have to engage, and this is time consuming for them. So they need to make available their technicians, their people to actually be on the ground with us to make the ground truths and the validation of their requirements. And this is where the agency has been helpful through the European Space Agency, through the INCUBE program, but at the same time, it highlights for me the problem with the bridge to the policymakers, which is we need to find a different mechanism to actually highlight how much this is worth in terms of value. And it's not just the value for money, it's the impact on risk assessment, on prevention, on civil protection, actionable information. And we've seen this with Christine and the storms that went through the country. We were asked to get data down from satellites, and the data was just simply not available. And it was not available because the satellites were not tasked, because we were not in prevention mode, so we were not contracted to do so. So there is a relationship there that needs to change, because it's not immediate. If there is a relationship, then that data can flow down much more simply, and then obviously the actionable information can flow. But there is a cost to that, and the first thing they'll ask is how much it's going to cost.
Well, I agree that we should bring decision makers to the conferences, but we should be very careful to what conference we bring them, because we need to understand what is the expectation of the people that is here. So if we want to have scientific discussion, we have the risk that they cannot follow the discussion, and in the end, the only thing they will ask is how much is then gonna cost. And that should be in the really end, when they understand what's involved on it. So I think, of course, that is probably the way, but we need a kind of the good or the proper conferences or the proper scientific forums to involve them, and so that they, again, understand, they believe it, they want it, and then we can answer the question, the price will be, it is.
Yes, thank you very much. So I will build on what you said, both of you. So one is, I totally agree that we needed to quantify or make substantial information of how worth it is. I was mentioning the example of the worth of the weather radar network in the US. It's $9 billion a year. If you don't have if you let the radar network die, there will be $9 billion per year in damages. So, and as that applies, that kind of exercise should be made in every country and for every community, the scientific community, I mean. Also, another thing that I have been banging my head against is about speaking the right language. So I am behind my computer, I come up with probabilistic products, and then I put them in front of forecasters. And there I am very, afraid that they won't get it. Some of them get it, some of them don't. I think it's a question of language. Our community, when we talk about uncertainty and how to communicate it, we have a strawman idea of what the user is. And we should probably stop doing that. Policymakers, emergency managers, business leaders they are used to managing risk better than we do. They deal with uncertainty all the time, and it is very substantial to them. What the language we are talking is probability and statistics. It's about the same object, but it's not the same language. And I'm talking the language of probability statistics. I'm not talking the language of an emergency manager. Not yet, at least. So.
Okay, I think we are on time, 5 minutes still, if someone wants to intervene. No. Okay, so maybe just a final word from each of you then before going to coffee break on what is the thing that you would like to change to have more impact by 2040, let's put it like that. So what do you think are maybe the lowest hanging fruits that we think we could take, and what could be the challenges more in the long term? Maybe someone wants to.
Okay, this is a tough one. I mean, for us, we are deploying a constellation of satellites. We come back to funding, of course, in terms of the challenges, but I think that's something that we'll overcome. By 2040, I would love to see the data really used in a more effective way, so that decisions are made with the information that's available. And I think, I mean, we came a long way, and if I see a weather forecast like 10 years ago, it's completely different than the forecast we have today in terms of uncertainty. That can only be improved by more data and improving the models. I think this is where we're aiming at, and this is also why I reinforce that we're making the data available for the community to work with, because we do want those models to be reinforced, and we are not the experts on those models. And then there is the data correlation, which I think is important. And again, we are not owners of the other data sets, so we need to work together. Cooperation is essential, and I think that's something that we will strive to do. And then if I can ask for something, obviously I'll ask for budget, but that's everything that will flow from that. There are areas that someone mentioned parametric insurance before. I think these are areas that we can see quick wins. The low-hanging fruit is there. We're working on that already, particularly with the forensic analysis for fraudulent claims. It's been a eye-opening experience because some of these things are sometimes blocked above in terms of the corruption levels, etc. Not in a European country, this has been in South America, but it's interesting because it has a massive impact. This relates to a flooding event in Rio Grande do Sul a couple of years ago, where basically 70% of the rice production of the year was wiped out. That has a massive impact in terms of commodities, in terms of price of rice in the global market that they had to negotiate with Indonesia and other countries, and has obviously, you are hugely aware that there's an impact in terms of food safety and all that. So those are the low-hanging fruits. I think we can use data to actually leverage that. And this is my 2 takes.
Well, in a very brief way, and from the community point of view, what I would like is that the people and communities have more information, have more knowledge, that the information and the knowledge passed to people and to communities. If I'm allowed to do this comparison, I would say that means that we are preparing the soil so that when the water comes, it can be absorbed by the soil in terms of knowledge and what is communities. So I think from my point of view and from the community point of view, I think that will be the most important.
Never waste a crisis. The crises are cascading, and it is making ever greater premiums on the work that you're doing. So I think there are great opportunities here to communicate your role in managing crises. Now that's a generality and a platitude, forgive me, but from the outside looking into this community, the value you have will only be greater over the next 15 years.
Thank you. So, low-hanging fruits. I think we can repurpose the language of uncertainty into talk about it in I highlight the upside. What can we do with uncertainty? We are always, we are uncomfortable with it. So changing that stance as a community, talking about it, I think is something we can do effectively. Second, as you were saying, there are
low-hanging fruits at, I would say maybe at the global level, the political level. WMO has programs, the United Nations have programs, like I think one is preventing disasters for all, is where we can increase our relevance. Finally, in 2040, that's an idea, but this is what I'm starting to think we could end up with practically is we may move away from many models, many products that try to, each of them trying to do everything, into a series of products that are specialized into meeting specific needs. So one product for extremes, one product for climate analysis, one product for water resources. And a user would ask ChatGPT, here's my problem. What kind of product should I use? And ChatGPT would say, use this product. And here's how to use it, by the way. That could be a way to reorganize our community toward science that is increasing its relevance and its visibility to the stakeholders. We can get into the weeds, into agencies, intercollaborations, and stuff like that, but I will, yeah, exactly. Sure. Lisa said.
Stop, okay. Sorry, I didn't see. Okay, so I think we can wrap up now. I think we heard about raising the relevance of the community and demonstrating the economic value. This economic value maybe should be demonstrated not just by the community, but the other sectors that will need this information to thrive. The engagement with society in general to be able to also pressure the policymakers to do the right decisions, and how to engage better policymakers and having both top-down but also focus on the bottom-up approach to make sure we develop the right products to the right people. And these might be different according to the different people we might have. So thank you very much for listening, and maybe now we can brainstorm during coffee break and enjoy the rest of the day. Thank you very much.
We can hear you.
Hi, I can. I would rather presents because I've changed to. Mhm. How's my volume? Is everything good? Okay, thank you.
check, check.
All right. Do we go? All right. You ready to start?
Yes.
Okay. Welcome everybody to the last session of the workshop. Mohammed, please take it away.
So, hello everyone. I hope you guys are now a bit energetic after the coffee break. So, let's start. My name is Mohammad Usman Liaquat, and today I am going to present one of our research activity regarding improving hydrological application through enhanced precipitation estimation from next generation gravity mission. I guess and I believe you guys already heard about the GRACE mission and its follow-on mission, which is providing the total water storage from regional to global scale. However, its temporal and spatial resolution is one of the challenging issue, making them problematic to interrupt the different gravity field products and ultimately its application in different hydrological applications. Like its current resolution is at, the temporal resolution is 1 month, 30 days, and the spatial resolution is 300 to 400 kilometers. Indeed, its downscale variants like MESCON solutions are available, but still they are problematic. Like the researchers and scientists are applying different machine learning, downscaling techniques to overcome these challenges. So the next generation magic mission and next generation gravity mission and mass change and geoscience international mission, the collaboration between ESA and NASA are the two upcoming missions to address these challenges in the future. Hence, the overall objective in this research activity is to examine how the improving spatial temporal resolution of these missions is useful to estimate the precipitation from regional to global scale. We all know that how the rainfall is measured. The journey is by the rain gauge and is being applied from many methods. However, this inverse water balance approach, which is already been developed by the LUCA from, I guess, more than 10 years ago, that the amount of water we have measured by soil moisture from below the soil surface. And this approach is already been, have been applied from last 10 years, more than 200 publications. So I will not go very in detail about this approach. But what we are doing in this approach that we are trying to update it as compared to, so the question may be arise, okay, if you have already very successful approach, why you are trying to use or update this approach? So this figure I'm just trying to explain it. For example, this soil moisture to rain is using like the soil moisture from the top few centimeters of the soil, and then to estimate the amount of rainfall. However, in this approach, it's not only like the total water storage is not only in considering the soil moisture, but it's also like the groundwater and subsurface, providing us a clear picture how the amount of water is not only moving across the land but also below the subsurface. So if you just see the bottom end picture, I've just tried to explain in very simple way. Like if the SM2 rain approach is using like like the skin of the surface, the body, then that TWS is considering like both the subsurface and surface parameters and making them like a whole body to examine it. Before moving next one, I would also like to important mention here that everything that we are considering here, because right now these missions are not launched. So this is that we have developed everything in the synthetic world, because you guys maybe later I will let you know how it will works. So about this configuration is at the moment, indeed, we don't have this high resolution data that is will definitely being launched by these missions. So we divided this activity into two parts. In the first part, we have developed this synthetic data by considering like the Era 5 land soil moisture and at the 4 different layers, like 4 layer which is starting from 0 up to the 289 centimeter, and then we consider it as like a total water storage. And these 4 layers we accumulated, making them from soil moisture to total water storage. And then the first step is like we are applying this approach at like the ERA 5 land at daily scale. I mean how it will, if this data from the current which is available at monthly, if we have at daily scale and 10 kilometer. And then we are aggregating it to special 5 day, which is the possibly the potential, the temporal resolution of these missions once it will be available. And then the first task is to check the performance, either this approach is able to simulate the precipitation or not. Once we check the performance of this approach, the next task is to add the noise in it to see once this mission are launched and how is the varying performance in terms of adding the error and how it is deteriorating the results. And the last step is we are, in terms of the future missions, we have the data from another project that we will introduce and see the performance from both regional and global scale. These are the error assessments of it. So the first results is about either this approach is like this TWS to rain approach is able to simulate the precipitation or not. The question like in forms of yes and no, and the answer is yes. Like we have, like first of all, as I have shown you, like at this one the results at daily scale, and then we have aggregated into the 15 days that I have mentioned here to for the clear visualization of the results. So overall the results exhibited satisfactory performance in terms of that the model is able to reproduce the precipitation by using the total water storage, as you have seen both spatially and temporally. And over the all Europe, except in some parts like in the northern Italy, Alps, or in Baltic countries, where we have a slight less performance. And this less performance is associated with definitely with snow accumulation, pre-thaw process, and delayed snow water storage phenomena. And also indeed in mountainous region, we have the orographic precipitation phenomena that is basically, is deteriorating the performance in these regions. But overall, we can say like the higher correlation, if you see the blue color here, is mostly prevailing in throughout the Europe, and lower RMSC, that is basically align and support our results in terms that the total water storage is able to reproduce the precipitation. Similarly, this is also very important figure is about where we are always like have a more focus that the temporal resolution have a more impact than spatial resolution. So if you see like at 5 day, the results have a higher correlation even after adding the error that we have. I have mentioned in my previous slides that sorry, this one, yeah, these are the errors that we have introduced, like 0 error, no error, 1.9, and these errors are basically according to the missions that we have introduced in it. So you can see that with 5 day, even by adding the adder, the model exhibited the better performance. And these results are, we took it 100 random points throughout the Europe and then take a mean over there. As compared to if we are seeing like at the coarser resolution at temporal 30 day, even without error, the results are exhibited lower performance, both in terms of the correlation and higher RMSE. So these are the results also that's for us that if we have a better temporal resolution, that exhibited better performance as compared to the coarser resolution. And then these are the spatially analysis that I have mentioned before, that at 5 days 0 error, and consequently as we are introducing the error like 1.9, 4.2 according to the missions, that how the results are deteriorating once these by adding the errors, and the performance of these precipitation is getting lower. So without error, and then how these errors are reducing the performance. Yes, these are the results that from another project funded by the European Space Agency. It's called as SYNC project, where we got the data from our project partners, synthetic data, in terms of, we have indeed like filter and filter configuration, but here I'm more focusing for the filter configuration because they exhibited better performance. In terms of gray C, NGGM and MAGIC, here like you can see the scaling from 0 to 100, and the red values are showing the better performance. Especially I would like to concentrate in the Central Africa, North America and South Asia, where we have a very significant improvement in the results, because these are the regions that we are discussing from the last 2 years, data scarce regions. So it means that this perform a very significant or good performance in these regions. So it means that these missions will have a very good performance, especially in these regions, through exhibited a better performance in data scarcity, where we every time we have the problem regarding the availability of data and how to apply the different techniques to get a good results in these regions. And additionally, we also check the performance of these missions with comparison with the gray sea, how like these missions, like the relative performance. So of these missions from like MAGIC and NGGM with respect to the gray sea. So this is like the simple correlation difference that and this difference also support our results that relative improvement especially demonstrated the added value of these missions, especially if you see the blue values, blue colors, like in the upper high altitude northern regions, and that they exhibited the better performance. Indeed, also in the Central Africa or North America, North South Asia, they have, I mean, also like a very low, not a low, like a very reduced, like a very low biases, low differences in there, which ultimately also supports our results and give a very strong support for these missions. Last but not least, maybe there are some questions arises about did you guys also check the performance with the current state-of-the-art product? And the answer is yes. We also check the performance with the current state-of-the-art, such as the one of the product developed by the Luca SM2 Rain SCAT and also the GPM, where again this mission have exhibited better performance as compared to the current state-of-the-art product, especially if you see the blue colors like in the Central Africa, Northern America and North South Asia, and also some of the regions in South Asia as well, where these this mission, the NGGM especially exhibited better performance in terms of correlation difference. And these results also support our added value for these missions, that once these missions will launch, will give us a quite significant improvement in terms of both precipitation and also for the other hydrological fluxes as well. So the take-home message from my presentation is, first of all, either TWS, total water storage, is able to reproduce the precipitation. So the answer is yes. After this SM2 rain, we are able, by using this total water storage, to reproduce the precipitation. And the next is the filter configuration, especially the MAGIC have a better performance followed by the NGGM in gray sea to retrieve the precipitation. And in terms of, if I say like the relative performance, the NGGM and MAGIC provide the better performance as compared to gray sea, increasing the R square greater than 40%, especially from the state-of-the-art products that I have already, show you in our previous slides. And our results, and we are strongly, you can say like the pushing or supporting that the higher temporal resolution, 5-day or better, would be really beneficial to ensure the precise precipitation from the future gravity mission that ultimately is being used for hydrological fluxes estimation. Yes, so that is from my side, and then floor is yours to ask the questions.
Yeah, I wonder if you could clarify a little bit. Especially with the GRACE itself, your maps seem to have resolutions of like 50 kilometers, which is not really possible with GRACE.
With 50?
So,
no, sorry, I didn't.
So you were showing maps of correlations in preset GRACE, and then the next gen. Yeah, like for instance.
This one, yeah.
Yeah, they have. You have 50 or better kilometer resolution.
This one is available at 1 degree.
But GRACE doesn't come close to 1 degree resolution. It's like 400 or 500 kilometers. So where does this? How do you get such high resolution out of GRACE data? Is my question. Are these all simulations or real?
No. These are all the synthetic data that we use it.
Okay, so you're doing it at 1 degree.
Yes,
okay.
yes.
I think, Mohammed, we better cut there due to time.
Okay.
Because we went a little late. So, is that okay? Are you okay? Yeah, okay. Yeah, sorry, I have to be a little bad cop because we got a lot of talk.
Okay, thank you.
Next talk is going to be online. Vasco is going to talk? No. Are you ready, Eric? Sure. Okay.
How's that? Can you hear me? Am I good? Okay. So hello, everyone. My name is Eric Shearer. I'm a research civil engineer with the U.S. Army Research and Development Lab. I'm going to present the precipitation forecast related work our team has been doing for the FERO screening process. And actually, really quick, let me turn on my camera. So the Forecast Informed Reservoir Operations Project, or FERO, is an effort within the Army Corps of Engineers to introduce advanced weather and water forecasting into a dam and reservoir system's legal operating documents to create a flexible, quote-unquote, FERO space that can bolster water management goals like flood risk management, water availability, water quality, among others. More simply, if you take flood risk management, if a water manager knows a large storm is coming, FERO allows them to start releasing water ahead of a storm rather than waiting for measurements of water on the ground, i.e. stream gauges, which have been USA's policy up to this point. On the other hand, if you can reliably predict dry conditions, excess water in your dam no longer represent a flood risk and can be held onto into the dry season. We've already seen this in Mendocino and Prado in California, which respectively have saved tens of thousands of homes worth of water during wet years. So right now we have 8 FERO sites in varying stages of the FERO viability assessment. How that works is we start with identifying a site, identifying the studies that need to go into it to do FERO. This is the work plan. Creating a final document of these results, the viability assessment. Here we have work plan to study underway and viability assessment as study complete. Once that's done, we can take that document and use it to update the dam reservoirs water control manual, and that's the legal document that dictates how dams that are operated within the Army Corps. So far we've only been looking in the West Coast, but the question remains, where else could FERO work? This is not only our question, but also a request from Congress who wants a national prioritization list for future FERO viability assessment funding. So to do this, we have created the FERO screening process. And the FERO screening process is a high-level assessment of FERO suitability at all USA's regulated dams. It's a multifaceted assessment. It's not just forecast skill. So this includes, does the site have a legal control document? Does it have an operating gate? Is flood risk management a stated purpose? So this is done through a 3-step approach involving engagement with district staff the whole way through. And we are trying to identify where FERO is not currently possible, trying to figure out potential benefit across the Army Corps with FERO, and trying to provide recommendations for next steps. So our FERO forecast evaluations are following down this roadmap, of which I'll go over each one individually. But the first step in the FERO screening process forecast skill evaluation are stage A calculations of relevant lead time and binary evaluations of leverageable skill. And again, I apologize for the speed I'm going through this. This could really be like a 2-hour talk. So forecast skill is integrated into stage A through a 2-part test. We consider inflow forecasts identified directly by the districts. On the other hand, stage A also considers precipitation forecast skill. Precipitation forecast skill is calculated with our university partners at CW3 and UC San Diego, along with ourselves. To calculate precipitation forecast skill, we assume a target FIRA space of 5% of the gross pool and calculate a required forecast lead time based on the amount of time it takes the site to release its target FIRA space and then have it travel past its first downstream control point or downstream flow target. This relevant lead time is where we do our calculations of the critical success index, shown on the screen in front. Here it's just the 1 day, but for our sites, we're doing it dependent on the hydraulic considerations. If skill is above 0.33, the value, which is the value of random chance, then we consider the site has sufficient precipitation forecast skill. This is just a binary yes/no. If both indicate that there is sufficient forecast skill, then forecast skill is considered a standard barrier. If there's disagreement, one says yes, the other says no, then it's flagged with significant issues. And if both are no, then we say that it's a prohibitive barrier and the site should not be recommended for the next steps. Here's the final results of stage A with all considerations, not just forecast skill. I don't have time to get into it, but I did want to note that there's good representation of the dams across the three categories. Sites with yellow or green designations generally indicate where stage B evaluations can occur. That's meaning that they have identified inflow or precipitation forecast skill based on their previous slide. So the sites that move on to stage B go through a three-prong evaluation of forecast skill that considers the wet, dry, and hydrologically linked forecast skill at the site. Really quickly, to just summarize stage B is the deeper dive into all aspects of water management that need to be considered for FIRO. Is there a collaborative spirit with your stakeholders? Do you have endangered species that necessitate strict operational procedures? Are you currently being sued? These are all collapsed into a benefits versus level of effort score. But last, forecast skills evaluated using the aforementioned three-pronged approach. The three metrics are evaluated and collapsed into a forecast skill adjustment, and that adjustment can increase or decrease the total score that is reported out to the districts along with the recommendation for future FIRO activities. The stage B scores are reported out in what we call stage C dialogues, but the stage B and stage C are really an iterative process. Stage B evaluations can be adjusted based on suggestions made during stage C, including aspects of forecast skill evaluations. For example, changing the relevant lead time or the FIRO space assumptions. So this is our three-pronged approach to forecast skill evaluation. Unlike the binary yes/no of stage A, each one of these gets a score, and those three scores are collapsed into that forecast skill adjustment. First is the critical success index. It's the same calculation as stage A, but rather than yes/no, we have a score. This is done forecasting extremes at the 95th percentile out to the relevant lead time. We also have the dry forecast failure ratio that asks the question of how often are dry forecast evaluations out to forecast lead times of relevance very wrong. Here we've chosen a lead time of 5 days, so it's 5 days across the board, and consider a dry forecast to be very wrong to be when observations that day are greater than the 90th percentile of rainy days. So dry forecast, a lot of rain. Error tolerance is our hydrology-linked forecast evaluation. It asks the question, how well can a site handle errors in the forecast? That is, during multiple consecutive days of large under-forecast error, how many days does precipitation error converted to inflow error using watershed area and a wet condition runoff ratio fit the site's flood control space? This metric allows us to calculate a nice round number of days that we can tell a water manager they have forecast skill out to. There are a lot of assumptions and design choices we've made that have kind of created limitations in our forecast evaluation. To address this, we have done some robustness testing. This includes looking at the relevant watershed size that we're doing the calculations over. We're evaluating at the most representative HUC 8, HUC 6, and the direct drainage basin based on GIS watershed segmentation. We're also looking at the travel and the relevant lead time and how much that can be changed based on different assumptions, including aerospace, or if there's more relevant downstream control points than the ones we've identified. That's for the previous point. And also looking at the differences in QPE. We're only considering the GEFS reforecast data set as our forecast data, and that's just the control number. But we are looking at both PRISM and Stage 4 to see the differences between them. And all of this information is reported out in Stage B, so the districts are aware of all this robustness testing going on. So we are currently in the midst of calculating Stage B across the US. Here are the results for the South Pacific Division, think the Southwest US. Well, I'm not going to go into the specifics. You can see the number that fell into each recommendation category on the left and the forecast skill scores in the chart on the right. Currently, we're evaluating the Northwestern Division and the South Atlantic Division, think the Northwest and Southeast of the country. Next year, we'll be evaluating the Northeast and center of the US. And then we recognize that there are many ways that FURO can work beyond yearly evaluations of skill, all precipitation. So perhaps only for the winter, or perhaps only for certain kinds of storms. Our university partners at CW3 are evaluating the skill of more targeted forecasts. These evaluations are not part of Stage B currently, but they can be the subject of future communications and FURO suitability score updates. First one of these is cool season precipitation. Here we see a significant improvement in skill when only considering cool season. I believe this is November through April, but I might be wrong, but I'm pretty sure it's those 5 months. And then pretty much universal improvements in skill across the country, except for some regions in the middle of the country where the seasonality precipitation is more in those fall, spring months. That kind of splits the precipitation across where we've decided to segment it. And we're also looking at storm typing. So we're looking at atmospheric rivers on the left, which show pretty universal increase in forecast skill, and cutoff flows to the right, which show a mixed increase of forecast skill depending on where you are, but definitely a significant improvement in the middle of the country, which is one of the regions that we have significant issues with. So I want to say thank you. Please, if you have any questions, and I'm sure there are plenty given how fast I had to go through this, please reach out to myself, Elissa Yates, who is the FURO screening process PI, or Carrie Talbot, who's the USA FURO program national lead. And if you're interested in our interactive story map, please scan the code on the right.
Great. Thanks so much, Eric. We have time for just one question, and then Daniel come up for the next one. Do we have a question? Okay, we just gained a minute. Thanks so much, Eric, for that fantastic talk.
Thank you.
Yeah, thank you, Eric.
Sorry. Good morning. My name is Daniel Waters. I'm going to talk to you about an extreme precipitation event database for the contiguous US. I'd like to acknowledge my co-authors before beginning. Okay, overview of the talk. So the aim is to produce a sub-hourly extreme precipitation event database for the contiguous US. The idea behind the project is that it is in collaboration with NOAA, so the database itself is designed to mutually support a newly developed geospatial probabilistic estimation package, which is produced by our colleagues at NCAR. It provides daily precipitation and temperature estimates, ensemble estimates. But the sub-hourly extreme precipitation event database, as well as being advantageous for NOAA, has many advantages to the community as well, beyond its original design. The novelties of the precipitation event database are as follows. It will be the first database to quantify the record of US extreme precipitation events. We see it as being able to bridge in-depth and consistent process characterization from sub-hourly all the way up to daily timescales. So we're really able to get at the temporal changes or temporal evolution of these extreme events. The benefits, we see it as being beneficial for studying extreme precipitation processes in high spatiotemporal resolution. It can be used to evaluate models and new precipitation data sets. We see it as definitely being advantageous for validating spaceborne precipitation retrievals from a process perspective, and it can be used for supporting emergency management. Okay, so just a bit of a primer on MRMS. MRMS is a mosaic of ground-based radars across the US, gauges with model input. It provides outputs at 0.01 degrees resolution every 2 minutes. Okay, so the method for the database. This slide gives a good summary of what we're trying to do here. We want to be able to automatically detect extreme events at the daily scale, such as the Texas floods that you're seeing on the left-hand side here. So that's the daily accumulation back on July 4th of last year. And then be able to go into the event. So basically go to finer temporal resolutions to understand the evolution of that extreme event, both at the hourly scale and the 2-minute scale, and provide that detailed diagnosis. So I'm going to show you a bit of an overview of a single case study. We've taken the Texas floods as an example to show you kind of the sort of information that can be extracted from this extreme event database. So for the following slides, you'll see on the left-hand side, we've got the whole picture of the contiguous US, and on the right-hand side, we'll focus on Texas, where that extreme event was. On the contiguous US side, you can see the accumulation across the 10-day period of the Texas floods, and we can see that in the Texas region there was severe precipitation there. As we focus in a bit closer, you can see that in the Hill County region, the maximum accumulation got up to close to a meter of rain. You can then convert that to the volume of precipitation just by using the 1 kilometer by 1 kilometer spatial resolution. And when you look at the volume of precipitation, then you're able to see that it's over 1 kilometer cubed of rainfall. In terms of occurrence then, this is where things get interesting, where you really start to get into the diagnosis. We provide accumulations, you see that regularly. But occurrence is something that's quite interesting and a key characteristic of an extreme precipitation event. And this is where we start to learn more about the Texas floods. So looking at the occurrence here, you can see that flicking between the two slides, there's a lot of precipitation, but where there was the maximum rainfall, that was where there was principally the most occurrence of the rainfall. So in the outer regions of Texas, where there was a lot of rainfall as well, it was less than kind of 1% precipitation, or 10% precipitation, I should say, during the 10-day period. But you can see that in the center of the Hill County region, we're getting up to like 40% of the time there was rainfall. That's across a 10-day period. So that means that about 4 of the 10 days aggregated, there was rainfall in that area, which is a lot. Then we can get into the typology, and this is kind of touching on a previous talk I gave a few days ago. But we can start to split the event by convective accumulation and by stratiform accumulation then. Why is this important? Because we're getting into the energetics of the system, which means that the processes are different. So we're able to learn more about the event itself based off of the microphysical processes, rather than just the fact that an event occurred. If you look at the breakdown, what's pretty interesting is where the extreme event was occurring, about half of it was coming from convective accumulation, half of it was from stratiform. Okay. Then we look at the contribution of the rainfall And you can see here that you can almost split the event in two. So there's almost like a western component of the event and an eastern component. If you look at the western component, it's principally convective. But on the eastern component, it's principally stratiform. And that provides a great jumping off point for things like satellite validation, for process studies, for looking into the microphysics. Because that's quite an interesting case. Why would the event be split into two different precipitation types? Okay, in terms of future work, so I've shown the potential of an extreme event database for a single prominent case study from last year where it caused significant flooding in the US and caused a lot of fatalities in an overnight period as well. What we're looking at in terms of future work is to provide more sub-daily extractions, so give information on the maximum rainfall across different timescales. So that's both at the 2-minute timescale, hourly and daily intensity. We will also provide percentiles of the precipitation characteristics and information on system evolution as well. One of the key advantages of MRMS is that ability to look at the evolution of precipitation events, and in particular to get it at fine spatial temporal resolution. So we're able to really get into diagnosing them, looking at things like the temporal evolution. If you look on the right-hand side here, the video is showing Hurricane Harvey, and you can see that there's quite some evolution in that event. Looking at things like the distance traveled by the storms, the size, the periods, etc. And at present, we are working on a variety of ways to create automatic detections of these extreme events. The idea is that we'll identify them at the daily scale, provide a net CDF product that can be used by the community to go into that event, and then provide a range of key metrics that can be used to, for you to evaluate your satellite products, for you to go into your microphysical process studies, for emergency management, etc. Okay, thank you for listening.
Fantastic, great talk. Question?
Hey, Daniel, I'm wondering about, you mentioned a little bit at the end how you might distribute the case list or whatever you have. So can you explain a little bit about, because if I want to have access to all these extreme precipitation events and all the data that you have, what is the format of that? You know, is it going to be like a spreadsheet, or is it going to be just NetCDF files, or what's the actual format that someone like me can actually use? And then I'm wondering about also, there's just one or two talks about the impact of downdrafts on extreme precipitation. I think we really need to understand whether these extreme precipitation events are being enhanced by downdrafts. So if we could have that information as well, that'd be really useful.
Okay, thank you for your comments and questions, Lee. In terms of the first one, in terms of format, we anticipate it's going to be a NetCDF format that's output. It makes it ideal for providing kind of geospatial information for a variety of different variables. So you'll get things like your accumulation, you'll be able to compute volume very easily, but then we'll really get into kind of the sub-hourly and hourly kind of different metrics that can be used for a variety of different reasons. In terms of your second point about extremes, this provides an opportunity to easily access these extremes from kind of radar gauge mosaic in MRMS that can be widely used then. So it really gives an opportunity to kind of get into the characterization of the extremes in a way that hasn't been maybe uniformly done previously, at least over the US. Does that answer your questions? Cheers, thank you.
Hey Daniel, great talk. And two, I applaud you for all the things that you're involved in, because wow. So one of the things that has come up, and I learned about at AMS, and also Pierre talked about, is we're moving towards radars. A lot of radars are going to be going out, and they already are. They're getting old. And so how is this work going to be kind of pushed into the future if we're losing our radars? And I know there's a big push to be able to provide better or smaller in different places, et cetera. But how might we deal with that moving to the future? Because I think this is a great idea.
Yeah, that's a really good point, Jessica. We are, in some ways, we work in a chain, okay? So we're beholden to what comes before us. In this case, we're beholden to what MRMS looks like in the future. I can say that in terms of the future of MRMS, things are going to change. There's now commercial ground-based radars that are coming into play. That's not been touched on so much in this conference so far. But these are things that are coming in the future, as well as the spaceborne side of things. We've also got ground-based commercial coming in as well. And that's a problem for MRMS to solve. In particular, there'll be new radar frequencies for the first time. The US network is S-band, but there's going to be integration of X-band as well. And, that requires a lot of work. In terms of what we're doing and how does that evolve with the upgrades to MRMS and maybe potentially big changes to MRMS, especially as the next generation of weather radars come along. What I would say is that we have a good record of MRMS so far. That thankfully, maybe in some ways, fortunistically, is at the same time period as a lot of the spaceborne information that we've got, and there's still a lot we can learn. Just like how we've used TRIM, and we keep going back to TRIM, we can keep going back to this almost like golden era in some ways. But the idea will be this product, as future evolves, as there's more MRMS, we produce more of these extreme events. But our role, providing the data, will also be maybe that traffic light system of like, hey, things are changing, you need to be aware of this. Because if people are going to go and use this stuff, we don't want them to be using it blindly.
Okay, so actually it is just to complement the excellent answers from Daniel. Regarding your question on updraft and downdraft, we may look into ZDR columns and KDP cores, which are experimental products in MRMS and are graded, but we need to figure out if those are reliable information that we can easily convey in the same manner. Otherwise, in Norman, there is a sensor that is being developed that I think will be very relevant, which is called passive receivers. So basically it's a passive radar that can piggyback on the transmitters that are next rad and allows you to retrieve 3D winds. So in the future, we can envision that there will be 3D wind information, like there is 3D reflectivity information, and that would be a game changer for characterization of extremes, where you can get way more direct access to convective mass fluxes, etc. So that's something we are. So those are two options, short term, longer term, that we are aiming at. To answer your question about continuity, so the MRMS team has been thinking for years about creating a reanalysis, and this is complicated. I will not get into the weeds, but they have an ongoing effort in order to generate that. As far as the replacement of the radar network is concerned, the National Weather Service, leading that effort, wants to use the MRMS system as a cornerstone of this effort, and they are very concerned about the continuity and consistency of the products that are generated and delivered, and that we are using for this database.
Apologies for missing part of your question, Lee. I struggled to hear. So thank you for answering it, Pierre. Apologies.
Okay, thanks, Daniel.
Cheers.
That was great. Okay, can our next speaker come up? Or is it on? Is it remote? Oh, okay. Okay, David Tweedy is now going to speak to us about convection, convergence, cyclogenesis, injection.
Just page, okay. Up and down. Yeah, my research has been involved with extratropical cyclones,
and convection, and mainly how convection impacts them. And the premise of my talk is going to be that certain extratropical cyclones are going to intensify as a result of a nascent instability. And by nascent, I mean it's impending and self-sustaining. And convection has a role in this, and I'm calling it convection instability of a nascent kind or sink. Basically, I'm looking at a subset of these storms, and Binder and his team studied 35 years worth of Northern Hemisphere data, and they identified different categories. The category I'm looking at involves 500 out of the 5,000 storms that they identified that were explosively deepening and had a strong warm conveyor belt, which you could call an atmospheric river. So there's a storm that occurred at the end of October 2017. This is the 500 millibar chart preceding this storm development. And you can see it's a pretty north-south orientated trough. 12 hours after that chart, the 24-hour precip using stage 4 precipitation is shown here. The part that I'm focusing on is right along the coast where there was up to an inch or so. Not so much focused in Florida, where there was over 2 inches and sometimes 4, or the Appalachians itself. But this is 24 hours worth of precip. The following 24 hours, you see this. To give you an example, the entire state of New Jersey averaged over 4 inches of precip in this 24-hour period. And the period could really be reduced to about 16 hours. A massive amount of precipitation. 24 hours following that, you can see that most of the precip is spent. Not much happening. I was going to try to show you that, I was going to try to prove there was a warm conveyor belt, but in this case, because of the extreme situation, a mesoscale precipitation discussion occurred. And the analyst wrote that up to a 250 nautical mile wide plume of over 1.5 inches of precip was embedded in a warm conveyor belt. So most of the precip occurs in a convection zone ahead of the cold front and coincident with a warm conveyor belt flow. It obviously has a lot of convective instability and a range of cell sizes from mesoscale complexes to individual cells. It defines an area of average descent, and this implies horizontal convergence in the boundary layer. To give an example of a schematic, the small convection shown in an individual complex is donated by B. The aggregate average convergence is shown by A, and kind of bounds the whole thing, and the conveyor belt flows are shown by red arrows. So this occurs when strong southerly winds are present above the boundary layer in the free convection zone. Downdrafts occur that are from different sources, cumulus-related, subcloud, cold pools, etc. Downdrafts have to transfer momentum down gradient into the boundary layer. And if the direction of the transport is correct, it's going to increase the advection of low-level, higher potential temperature. And this sustains or increases convective instability, and this is the feedback effect that causes the instability. In addition, the convective boundary layer is a source of growing convective plumes due to Reynolds stress-created turbulent kinetic energy. Normally, that energy is consumed by, I'm trying to say here, it's consumed by viscosity. The presence of those plumes increases convective efficiency. So if you have a lot of plumes rising at the top of the boundary layer, and you have convective instability, you're going to get convection. So let's go back and look at our storm. On the East Coast, you can see the surface low 12 hours after that 500 millibar chart. You see very weak low on the East Coast. At 8:50, you see a south-southeasterly flow above that low pressure area. 700 millibar chart shows southerly flow. 12 hours later, the low pressure is finally getting going. The 850, some hint of circulation there. 700, not so much. 12 hours later, we see a very intense low. And now the 850 is fully involved, and even the 700 flow is getting into the act. So, since the low pressure is characterized by convergence itself, continued pumping of low-density air in the conveyor belt forces the density gradient to grow vertically. So you keep pumping low-density air in, it's got to grow vertically. If the synoptic scale trough remains quasi-stationary, the pumping is going to continue to cause intensification. From my research, I'm suggesting 3 short waves, baryclinic short waves, are required to produce a bomb cyclone. And these can become cut-off flows. So, whoops, I skipped one. So sink instability seems to play a role in extratropical cyclones, but they play a role also in tropical cyclones. I think they do. China Liaison, in their famous paper, stated that hurricanes are observed to develop from pre-existing tropical depressions that have somehow acquired a degree of circular symmetry and a warm core. However, these disturbances are rare. They are typically asymmetric and possess a cold core. And Berkeley discovered, and he did his research, that the 700 millibar level was the maximum trough intensity, and it was a cold core, and it was asymmetric. And Gray, in his studies, once remarked that the transition from the cold core to a warm core in a tropical cyclone ultimately requires convergence to a center. Here's an example, an artist's rendition of an African easterly wave. On the left side, you see the dashed line. That's the trough axis. The blue indicates meridional winds flowing from the north, 2 meters per second plus, and the red from the opposite direction. Here's another example of a composite trough. In the middle of the diagram, the winds ahead of the trough are really northeast, about over 5 meters per second. These are streamlines. And on the eastern edge of the trough in the opposite direction. So how does this sink instability cause these tropical depressions to turn into tropical cyclones? Well, the cold core promotes convection, and we know that convection is prominent in waves that become tropical cyclones. In addition, convective instability, which may be initially weak because the assistants are rather weak initially, the downward momentum transport is only required through a 3-kilometer layer, so you can get transport of momentum in a relatively short time, even with weak convection. The asymmetry increases the probability of opposing boundary layer flows as a result of sink instability. Here's an example. If the African easterly wave has convection shown in those 2 circles that predominate over a period of time, then sink instability will produce boundary layer flows outlined in red, coupled with equity veering at 12 degrees. Only 1 out of 6 of the easterly waves undergoes the transition. More convection increases the probability. It may take a week or more to happen. The process is somewhat random, obviously. And the indication that the transition has occurred is the convective tops at the center are much higher than they were earlier. The lower density column at the center lowers pressure and creates a warm core. There's a great deal of discussion on outer bands, how they're created. I did a lot of reading the past few months, and it's kind of dismal. But a mature tropical cyclone manifests a very cold upper air flow outward. So this divergence, this is a mass conversion, it's a mass transfer issue. You get a lot of mass flowing into the bottom of the cyclone, and you have to have compensating mass going out the top. You can see this in the satellite imagery. They're mostly ice crystals flowing out, and it's kind of interesting. Cold outflow actually occurs for quite a distance away from the tropical storm center, and it creates increases the probability of convective instability. And SST gradients also would increase that convective instability. So Reynolds stress generated turbulent kinetic energy, extracts heat and moisture from the ocean top levels, and this increases convective instability. So that's the sink instability occurring again. Here's an artist's rendition of a storm overtaking an SST gradient. And here's a schematic that kind of shows how sink instability could work. A vector shows the geostrophic flow at the anvil level. B is the projection of the transport of that momentum to the boundary layer. That can be broken into two components. A component parallel to the band, which is C, and a component perpendicular. But the perpendicular component is largely compensated for by convergence itself. But convergence also actually conserves the long band component, producing like a warm conveyor belt flow F. You can see this in the winds that long band winds in these storms are much stronger, going from 10 to up to 30 or more meters per second in the boundary layer. And so this is how I believe these bands are being created. So to summarize, a mature tropical cyclone can be construed as scavenging for favorably orientated SST gradients from which it can produce sink instability that forms the outer bands, which eventually actually satisfy its need for energy. That concludes my talk.
Thanks, David. That was great. We have time for one question. Do you have a question?
Hi, thank you for the presentation. I am wondering, sorry, there are a ton of cyclones that are being created now, for example, closer to Europe. They start off as kind of TC, kind of extratropical cyclones, and then develop into TC, and eventually they achieve a bomb phase when they reach land. Do you think this sink instability is also responsible for these cases, for example, in the western coast of Europe or even the US?
So it's a question about, do they continue over land?
No. If this sink instability motivates these cyclones to achieve even more energy that we are observing in the last decades.
Well, yeah, most of the energy ultimately comes from the ocean surface, or large body of water surface. It's extracted from, the heat and moisture are extracted actually at the surface, and then the boundary layer, as long as this instability occurs, is regenerating this heat and moisture, and that's perpetuating the convective instability. It can occur over land for a certain time period if the upstream source of the ocean is close enough. I'm not sure I'm answering your question because of the echo in the room. I couldn't quite understand all of the question. Can you tell me?
Yeah, but then my second question is, how is the upstream energy source allowing this energy to be created in the cyclone itself?
Well, the proposition I'm proposing is that if boundary layer heat and moisture are transported, even we know that the warm conveyor belt is rising at the same time. However, if there's enough regeneration at the boundary layer, it's producing, it's keeping the convective instability quite high. And this can go on over land for a period of time. What's happening in the boundary layer is critical to this. If, for example, that trough I showed you was located 500 miles to the west, and I don't know if you are familiar with forecasting in eastern U.S., but the forecasters talk about a primary low and a secondary low. How many have heard that? Anybody? Anyway, the primary low cannot develop as much because the Appalachian mountains are too much of a barrier for the boundary layer mechanics to keep occurring properly, and so the warm conveyor belt can't sustain itself. If the large-scale trough was over Texas, then the Gulf moisture is still available and the heat, you can get the sink instability, the warm conveyor belt can go without much of an obstacle all the way to the northern part of the Midwest. And every 5 to 10 years we have the great Chicago blizzards. That's how they were formed.
Wait, we better stop there, Dave. Thank you so much. That was fantastic. Next speaker. Yeah, Chris. Vincent is coming up. He's going to talk about detecting rainfall events for agricultural fields using Sentinel-1 data.
Yes, thank you. Hi everyone, my name is Vincent. I work at Delft University of Technology in the Netherlands, and I will tell you something about my research on detecting rainfall events over agricultural fields using Sentinel-1 data in Ghana. So why Ghana? Well, this is a typical map showing the global distribution of synoptic weather stations, and you can see that there is a huge ground data gap in sub-Saharan Africa, including Ghana, which is why this region is highly dependent on satellites to make rainfall estimates. Thanks to a relatively new network of weather stations installed by the Trans-African Meteorological Observatory, or TAMO, we are now better able to compare satellite rainfall estimates with what falls on the ground. However, when we compare the two, we see that there's a huge mismatch between satellite rainfall products and the ground truth. So this is how data typically looks like in Ghana. So this is rainfall data from a TAMO station in Ghana together with data from iMerge. And you see that the high intensity events are generally underestimated by iMerge, while the number of events are highly overestimated. Why is this? Well, one very important reason why we think this is happening is because there is simply a scaling mismatch between a satellite rainfall product and a station. So when I show you these pictures, which I made during a field campaign, I think it makes sense why they differ. So we typically see very localized rainfall in Ghana or the subtropics, and the size of these storms are typically much smaller than the scale of common satellite rainfall products. So in Ghana, it's very common for rainfall to occur over a farmer's field, while locations only several kilometers away remain dry completely. So therefore, I'm investigating other sources of higher resolution satellite data to detect rainfall. I'm using data from Sentinel-1 for this, and Sentinel-1 is a European synthetic aperture radar satellite mission. And the backscatter signals that are measured are affected by surface roughness, soil moisture content, or vegetation. It is a very high spatial resolution of about 10 meters. When we zoom into Ghana, the revisit time of this data is typically about 6 days, but there are some overlapping swaths where more frequent data is available. So with Sentinel-1, we are able to make soil moisture estimates, and with soil moisture estimates, we can derive a QPE. But as I said, Sentinel-1 is a relatively low temporal resolution, so it may be too uncertain to make a QPE. And besides, most studies that use Sentinel-1 to make a soil moisture estimates, they use model-based or machine learning approaches, and they heavily rely on good quality rainfall data, which is something which is missing. And soil moisture data, of course, which is also very limited. So therefore, I'm investigating how to use Sentinel-1 data directly to make a rain-no-rain classifier. So yeah, that's what I did. I developed an approach to detect rainfall based on Sentinel-1 and a focus on agricultural fields in Ghana. So yeah, as I said, Sentinel-1 data enable us to look what happens at the level of agricultural fields, typically a hectare, for example. We can even see how the data varies within a field. So this is how a climatology of Sentinel-1 looks like for one of the fields at the left. And you can clearly see that the climatology follows wet and dry seasons in Ghana. And the variations that you see here are mostly driven by changes in volume or plant growth or soil moisture. However, instead of looking at the field as a whole, I made a climatology for every individual pixel within the field. And with this, you can say something about the relative backscatter of a pixel based on this long climatology. So data goes back until 2015 to now. I think the biggest strength of this, using this pixel-wise percentiles, is that you're much better able to compare between pixels within the field, but also between fields. So if we assume that short-term changes in backscatter are mostly driven by changes in soil moisture, we can say that in case a percentile of a pixel, when the percentile increases between two acquisitions, that this is driven by an increase in soil moisture and thus rainfall. This assumption mostly holds for agricultural fields around the rainy season onset when the vegetation is low and there's also not too much change. So if this works, we will have a data-driven method to say something about rainfall without relying too much on ground data. So now I want to show you how this works in practice. So I'll just highlight a few examples to show you the proof of concept. So let's zoom into one of the fields I've selected around one TAMO station. This is rainfall data of the station, highlighting the first serious rainfall in the year 2019. We had a Sentinel-1 acquisition a couple of days before this event, and you see that, so this map shows the percentiles, the pixel-wise percentiles, and you see that these are relatively low at the moment, so that this indicates that the field is dry. And then there was an acquisition right after this rainfall event. And you see that, the percentiles increased a lot, so this indicates that the field became wet. So based on this, we can say, we can assume that rain actually occurred at this field a couple of kilometers away from the TAMO station. And of course, this is a very clear example because the field was very wet because it just rained an hour before the acquisition. Another example, this is TAMO data for the same station for March 2025, and I'm highlighting two acquisitions. So there were two acquisitions on the 15th and one on the 20th of March, and almost no rain was measured by the station in this period, so we can expect that the field, the percentiles will remain low. But if I show you this, you see that the percentiles increase actually. So what happened? Well, when we include data from the satellite product, IMERGE again, we see that IMERGE estimated much more rainfall within this interval, about 20 millimeters versus 1 millimeter. So again, we can assume that the change of percentiles was actually again caused by rainfall. And I think this is a clear demonstration of how we can use Sentinel-1 data to bridge the gap between a point and a pixel rainfall estimate. Another example, this is a rainfall event of about 11 millimeters on the 4th of March in 2020. And we had an acquisition a couple of hours before this event and one a day later. So we expect the field will be wet. We're still looking at the same field. So based on this, the percentiles increased a bit, but not as much as we would expect maybe. If we include a look at the IMERGE data again, IMERGE estimated about 4 millimeters of rainfall. So maybe not as much rainfall as occurred on this field than was measured by the station, but it's a bit uncertain to say, to make a conclusion based on this. But if we then look at another field, outside this IMERGE pixel, we see that this field became much wetter actually. So maybe more rain has occurred at this location. But then if we look at IMERGE data, IMERGE estimated only 0.4 millimeters of rainfall, surprisingly. But I think still it's very likely that rain has occurred on this field as well. I only highlight very few examples here. But I must emphasize that the biggest uncertainty is related to this temporal resolution of Sentinel-1. So in case there's light rainfall in the beginning of the 6-day interval, it is very likely that this method, the signals are not strong enough to detect the rainfall by using Sentinel. So to conclude, there's a need for high-resolution rainfall information on ground level, and current satellite rainfall products fail to say something about this high spatial resolution of rainfall in Ghana. And using Sentinel-1, we can say something about the spatial variation, I think, of rainfall within the pixels of commonly used satellite rainfall products. As I said, this method is mostly applicable around the start of the rainy season, and at this moment, I think it should be used as a complement to other existing satellite rainfall products. So around the start of the rainy season, this is very valuable information for agricultural insurance, for example, germination insurance. Thank you.
Sorry, I have all the questions. This is interesting. I wonder about like evaporation and the time between things. Have you thought about taking other parameters, something that could give you more of the surface temperature or like some local characteristics to kind of tease out some of that to add to it, so you can kind of gauge whether or not they're actually like it's working as well as you think it's working? I don't know if that makes sense.
No, not yet, but as a next step, I'm planning to use cross-polarized data, so to say something about changes in the geometry of a field. So with this, we can filter out false alarms. But I haven't looked into temperature data yet, no. But no, thank you.
Yeah, nice talk. And actually, I've already seen this kind of stuff that you are doing. And I was wondering, yeah, I understand that you have a project in Ghana, but I was wondering why you didn't check first in a kind of synthetic study or in a kind of place where probably you can have a more dense Sentinel-1 observation. And also consider that, for instance, there is a potential plan of future mission in which we will have a Sentinel-1-like observation every 6 hours by using geostationary. This is a kind of dream for the future, but this kind of thing can be very applicable there.
Yeah, I've been planning for this for a long time to look at data-rich areas, but the field I showed you in this presentation is located in this overlapping swath, so there's more frequent data available here. And I couldn't show you in this presentation, but so in this case, when there's an overlapping swath, sometimes the revisit time is just 1 day, and then this method works really well. So yeah, I'm just hoping for more frequent data in Africa. Yes. Yeah.
Yeah. Just a quick comment. Andreas Fink at the Karlsruhe Institute of Technology has collaborated a lot with the university in Ghana, and they have a pretty good network that they've maintained over the years. So that would be a good person to reach out to.
Okay. Good.
Okay.
Thank you.
Great. Our next speaker is Spencer Jones. Is this a remote talk?
Yes.
Yes.
Can you hear me now? Okay, all right. Can you see the slides? All right, perfect. Well, good afternoon. My name is Spencer Jones. I am with Colorado State University. My PhD advisor is Chris Kumaro. And today I'm going to be talking about the current efforts in improving the training data for machine learning-based precipitation retrievals. This work really kind of arises out of two areas. Number one, the need to focus on better quality training data due to the fact that machine learning-based retrievals are a lot more sensitive than some retrieval techniques have been in the past. And I'll be kind of giving an example of that in just a moment. But it also arises from the need for a common training data set for all sensors. Currently, we have GPM, which has the radar and radiometer together on the same spacecraft, and so Other sensors in the passive microwave constellation can be fine-tuned to this, but we don't have GPM for all time, so this isn't actually possible for all sensors for all time. Just kind of as a either a refresher or a primer on kind of the physical basis of the Goddard profiling algorithm, if you're not familiar with it, the version 7 of gprof was a Bayesian scheme where we used a pre-computed database of hydrometeor profiles and their associated simulations in order to retrieve these hydrometeor profiles. And these are, the solution is assumed Gaussian, and so we use weighted means to do this. But in version 8, we have moved to a full machine learning-based retrieval for a convolutional and a 1D neural network, fully connected neural network-based solution. And so these do not use weighted means, and so therefore they can be more sensitive sometimes to inconsistencies or errors, even very subtle errors in the training data. Here's an example of this, and you'll see here, this is a landfalling tropical cyclone, and MRMS on the left, you know, the radar composite on the left, and then on the very right-hand panel, you can see version 7 of gprof, the Bayesian scheme that I mentioned earlier. And then in the middle, this was kind of a preliminary run. I believe the sensor is MHS here, but this is a preliminary run of the gprof neural network retrieval, and you can see kind of these splotchy areas of precipitation that really just kind of don't pass the eye test. And this turned out to be an inconsistency or a subtle error in the way that the simulations were created, which has since been corrected. But I just kind of wanted to you know, use this as an example for how, you know, very sensitive these machine learning types of retrievals are. And so I wanted to mention, by the way, too, that sometimes noise in the training data, but also noise in the simulations can, you know, cause these kind of errors, retrieval errors to happen. And so my first attempt is, you know, to kind of try to find and eliminate noisy artifacts that could show up in the simulation data. So that gives rise to the machine learning quality control algorithm. And in the interest of time, I'm not going to spend too much on this, but essentially the scheme is that you use n-1 channels to predict missing channels. And so you cycle through all of the channels doing this, and you get a predicted TB that has some kind of associated error with it. And this associated error, the prediction error, can be used to kind of show when these things can go wrong and kind of help us to find things like sensor anomalies and things like you know, maybe RFI and non-geophysical data, non-geophysical data errors. And so here's an example, or a couple of examples that I have here. One is the well-known channel failure of the 85 gigahertz channel on SSMI back in 1989. And you know, generally, it's kind of assumed to be good before January of 1989, when the level 1C product stopped reporting the 85 gigahertz brightness temperatures. But we actually, you know, ran this through the machine learning quality control algorithm, and you can actually see that these things start to degrade well before then. And then this is another example of, you know, kind of these, the red here in the bottom panel. This is SSMIS on F17, and these kind of red stripes that keep showing up on the right edge of the swath. And sure enough, this is kind of associated with a spike in precipitation on the right-hand side of the swath when you accumulate mean precipitation by scan position. And this was showing up as, you know, an artifact in the data as well. And so the next thing is the next effort, I guess, is to, you know, revisit the actual training data itself and how it's constructed. If you're unfamiliar with, again, with gprof, we use retrievals from the GPM combined algorithm, and it uses the radar and radiometer observations together, and uses an ensemble filter approach to try to get the one-dimensional optimal estimation solution by minimizing this cost function you have on the left. And I wanted to mention, by the way, that the radiometer and the radar resolution are very different. And so the radar resolution is generally around 5 kilometers, and the radiometer resolution is different for different channels, but it can range anywhere from about 32 kilometers down to much smaller than that. And so what they do is they downscale the radiometer resolution to the radar resolution in order to do the one-dimensional radiative transfer, and then use random variations and take the mean of all the closed solutions as the hydrometeor profile that was seen. However, one of the things that you do is, when you downscale using the approach that they do, you start to introduce noise, which actually makes it impossible to recover the original low resolution brightness temperatures of the radiometer when you re-average them together. And then you can kind of imagine a worst case scenario where you have high resolution footprints and low resolution footprints that are compared here on the bottom right. And these things are actually seeing different scenes. And so instead, my work is going to be trying to basically do the optimal estimation for the entire scene at once. So this would be a fully three-dimensional optimal estimation solution, which requires full 3D radiative transfer and, of course, large matrix inversions, which in the past have been prohibitive. However, we do have tools like machine learning that are able to handle the enormous amounts of radiative transfer computational costs and reduce them greatly. Here's an example of an emulator that we trained for GMI using CRTM, which is also this is the community radiative transfer model. It's also a 1D, a one-dimensional radiative transfer model. However, we do have this working for a pseudo three-dimensional radiative transfer model as well. And we have a manuscript for this currently in production. And you can see that these things are work really well. They're very fast. And they can also, introduce minimal errors, which are actually easy to quantify because we have the error data, where we have the errors against the test data, sorry. And so another thing that we have to kind of think about is, when you do a full 3D estimation, you have to have vertical correlations that we know exist in the precipitation systems. And so we kind of propose to do this by doing this in EOF space, or principal component space, for the hydrometeor profiles. And then you also have to take care of the horizontal correlations. And in this case, there's been a lot of promising work by Jackson Tan and others to have these algorithms like SPEEDY that are essentially these convolutional classifiers that are able to say, yes, this looks like a precipitation system that's real that I've seen in the training data before, or no, this doesn't look like a precipitation system that can really exist. And so we use things like this to be able to eliminate unlikely solutions and, help constrain the iteration process. So finally, kind of where are we? We currently have a manuscript in the second round of peer review for the machine learning-based quality control algorithm. And that code is available also on my GitHub if anybody is interested in downloading it and using it. And there's a pre-trained version for GMI, but there's instructions on how to train it for other sensors. We also have the manuscript currently in production for the 1D and pseudo three-dimensional radiative transfer emulator. And if you'll be at IPWG in a couple of weeks, you'll hear a lot more about that. And then we are, currently in the process of creating large numbers of high-resolution simulations in order to kind of get, these are cloud simulations, in order to kind of get a sense of the minimization and what the error covariances will constrain. And then we are in the process also of coupling the radiative transfer emulator to these high-resolution situations. That's it, and I'd like to thank NASA Finest for sponsoring this project, also the Department of Atmospheric Science at Colorado State University. Here's a link to the preprint of the quality control paper, and here's my email on the bottom left if you have any further questions or any more discussion. Thank you.
Thanks so much, Spencer. That was great work. Questions?
Thanks so much, Sanjay. That was great work. Question. Thanks so much, Sanjay. That was great work. Question. Thank you. Thank you.
Yeah.
All right, good morning again. So I'm going to talk about probabilistic quantitative precipitation estimation with spaceborne radars. I want to acknowledge Nana Liu involved in this project. And based off the discussion we had in the panel and the presentation by Spencer, I decided to focus a bit more on the probabilistic aspect than on other aspects. So you will be seeing me going through some slides quickly. So, well, no need to introduce GPM and DPR anymore. Thanks, Spencer, for that. The DPR is used to calibrate the constellation, the GPM constellation, but there are challenges in the interpretation of these observations, so reflectivity observations, for example, precipitation processes that we don't have access to directly, and also variability of precipitation within the footprint. So all that to say, for example, here, if you see that figure in the middle, it corresponds to an overpass of, let's say, the DPR over a precipitation system. So you can see on the background, this is real precipitation coming from MRMS that are created at every 1 kilometer. And on top of it, the circles are the footprints of the DPR scale. So you can see that none footprint is equal to the other. They all have their specific intermittency, precipitation intensity, and variability within the footprint. So it's a major challenge for retrieval. So I will pass on the guts of the algorithm, but there is a way they apply physics-based principles in order to interpret. But those principles do not factor well the variability within the footprint, for example. So we have a deterministic retrieval from space, but based off indirect and often underdetermined relations between the reflectivity observations and what we are looking for surface precipitation. For example, a single reflectivity value can be associated with 2 precipitation rates depending on what you sample in terms of particle size distribution here. So, for example, a few large drops may generate the same reflectivity value measured by the radar as a large number of small drops. And you will get very different precipitation rates in those 2 cases. And what I describe here, we talked about uncertainty a lot. It impacts remote sensing, atmospheric sciences, and hydrology. Precipitation variability is ignored. We deal with partially resolved or mixtures of precipitation processes within the sensor resolution volume. We have also limited characterization of extremes, and that limits our ability to apply the information from these sensors for impact. So deterministic estimation based on average property is inherently insufficient. Using uncertainty as an integral part of the precipitation estimation would be useful for data fusion, for data simulation, hazard information, and risk analysis if you're interested in the extremes. So this is where I'm going to focus a bit more. So let's say we have a reflectivity value that is sampled by a spaceborne radar. That's on the x-axis. And on the y-axis, you have the precipitation rate that you want to retrieve. Classically, especially on the ground, we apply what we call a DR relationship. It's deterministic.
But because of this variability, everything, every pair of reflectivity and rainfall rate values that fall outside of this curve are errors. And we have a lot of them. So the white space is a space of error, the white space outside the curve. Now imagine that instead you can see that as an ensemble of relationships, each of them associated with a specific likelihood. I prefer to see that as a conditional distribution of rainfall rates conditioned on the reflectivity value, conditioned on the observations. That's same object, different ways of interpreting it. But this time, the space that you have is a space of possibilities. So the thick black line here will be more likely than others. Still, that space here will be modeled. It has a likelihood of occurrence. Very rare, but it's possible. So now I give myself the possibility that for the given reflectivity value, let's say we have 35 dBz here, I can extract at that location the entire distribution of precipitation rates, and I can capture different processes, different particle size distributions that would be responsible for different precipitation rates. So what do we do with that? Well, first we can provide the entire distribution. That's increasing information content. Practically, we can depict the most likely value, that would be the median of the distribution, or we can use the expectation. If we want to capture the volume of precipitation for deterministic users in application, for example, in hydrology, this is what we would do, because we want to conserve the volume of water that passes from the sky onto the ground and at the surface. So that's what we get. If at every location here you see a map, that's an application of probability QP on ground-based radars. Typically, this is what we have, field of precipitation rates. And that's what we can still extract from PQPE. Now, the uncertainty can be defined as an interquantile range. So there are lots of debates on which quantiles to use. I would suggest that instead of figuring out whether we need to use a quantile 25 and 75, we needed to figure out what for, and maybe instead of starting from the rainfall rate values on the x-axis, maybe we should consider what likelihood do we want to capture within that interval range. It's like the 50% of possibilities that are the most likely around the mean that we want to capture. That is something that would be useful for data fusion and assimilation. Here, in the same field, you can generate from this interquantile value. So here in this case, I took 50% of the interquantile range, using 75% minus 25%. Then, if you are interested in extremes, you can investigate the likelihood of getting extreme values. So here, this is where it is interesting, because we were talking this morning about how a user can come up, has a situation, a use case. And I am figuring out here an excellent user. They came up with a single value that would be of their interest. So on the x-axis, this is the scale that represents the scale of possible scenarios. That vertical line here is what interests my user. For example, we were talking about parametric insurance. They define these thresholds, a single threshold above which they will pay the client if it happens. So with probabilistic QP, we can figure out the likelihood associated of crossing this threshold for given observation conditions. And well, there is a whole debate on what does it mean also for forecasters, because when you are working deterministically, as long as you are below that threshold, you may not worry about issuing a warning. But actually, without knowing, you might be very close. So that's, I will pass quickly on that. But this is a kind of map you can generate, the map of likelihood that you cross your threshold of interest. I told about an insurance company. It can be an emergency manager who knows that, for example, in this case, he's the watershed that he is monitoring would generate a flash flood and impact his city if there is more than 10 millimeter per hour falling on it. And we can do that for various thresholds very easily. Those computations are extremely fast, of course. So summary, that's what I wanted to highlight here, the information content, how to use it to make it relevant for stakeholders. So going back to the spaceborne radars. So there are, I think it might be relevant to what Spencer is after, because in this case, so we trained a probability QP approach based on radar DPR observations. But not only we extracted the reflectivity, but also their physical interpretation. It's my belief, and that's open for debate, that the physical interpretation carries some information that is useful for the retrieval. And a mixture of machine learning guided by physics might also be something we want to consider in the future. So I'm taking their interpretations of precipitation typologies, the incidence angle, the macrophysics. And you can see here an overpass corresponding to so Hurricane Matthew in North Carolina. On the left, you have the expectation that would be to be compared with their retrieval. But on the right, you have the uncertainty associated with these precipitation rates. So you can see that the uncertainty is higher at the edges of the swath. I don't know if you see also, but there are specific lines that enhance uncertainty closer to nadir. So that is also important to consider. And sporadically, you can see some spots, some specific pixels that are associated with enhanced uncertainty, probably because the physical algorithm diverged or didn't converge to a solution. So we could easily map them, discard these in order to build a database for training GPOF, for example. So I will pass on this quickly also. And well, if you apply the same framework and you get into the guts of the algorithm and how they interpret it, you can actually improve the algorithm. According to their parameters, you can significantly reduce their inherent biases. So I will pass on that quickly, scores, and I will get to the summary. So radars are a cornerstone for the global water cycle for estimating precipitation. And we needed to enrich we need to debias their estimates. We needed to enrich the information content we get from this. So this is an attempt at doing that. Thank you.
Pierre, so it's been a while since I've read your 2015 paper. Can you remind us how your approach works? How do you come up with these probabilities? Do you use a parametric approach or a non-parametric approach? I assume you may be using a Bayesian method as well. So if you could just remind me how you do that. To get the probabilities for the rain. Okay, great. And also, just a quick comment. I think and we can work on this, but I think that one of the things that you need to do, or we should try to do, is incorporate the actual microphysical equations that are used in the retrievals themselves. Because right now, it's totally divorced from, or it's mostly divorced from the, these are simplifications, obviously, but the actual processes themselves, the actual, the partial differential equations that are used in microphysics models are not really used. And we need to start thinking about ways of incorporating that information into these retrievals.
Okay, so the approach that they are using is not based on, so this is an algorithm that works operationally and that cannot afford using a 1D beam macrophysics model, which would run too slowly. Maybe with a surrogate machine learning model that would work.
Well, I'm thinking there's ways of doing it. That's what I'm thinking.
Sorry, what?
I think there's ways where you could use a BIM microphysics model to enhance, or even a more complicated, bulk model, essentially, and enhance these retrievals. But that's more theoretical work that we can talk about.
Yeah, I think there is a whole world where you can revisit this fantastic data set with more complex microphysics models. But that's a different topic.
Absolutely, thanks.
So speaking for Spencer for a second, the radiative when you talk about data fusion, right?
Yeah.
Surface rainfall doesn't have a radiometric signal at all.
Oh,
right?
Yes.
So what we really need is the drop size distributions and the horizontal distribution that you use in your PDF construct. I don't think we actually use specifically those, but that's really what we need.
Okay.
We will then use additional information to constrain the various solutions.
Right.
Ideal.
Okay. When I was talking about data simulation, it was data simulation of the retreat precipitation rates, which come with this uncertainty. But right now, this is a superficial suggestion to provide you with ways to filter out cases that you don't even want to consider, maybe because there's too much non-uniform beam thinning, or there are those complicating factors that even machine learning might not resolve well.
Okay, one more. Quick question.
Yeah, thanks for the talk. I feel like you, right? You looked mostly correctly at the uncertainty and the ZR relationship, right? That was most of what you talked about.
You correct the conditional bias and you enhance well, in this case, that would be the RDM relationship in the algorithm, yes. By providing, making it probabilistic, yes.
Yeah, but I mean, if you think about estimating precipitation of space, you have hydrometeors all the way above, you have the atmospheric background. Do you have right, I mean, this is just a part of the uncertainty. Do you have a budget that allows you, is this really the primary part of the uncertainty that we ultimately have?
Well, in this case, you can start with these parameters that they have in the algorithm, but okay, I can, a preliminary attempt we had is to ingest additional information, for example, precipitation type, which is estimated from looking at the interior profile or the gradients around the horizontal gradients around the profiles, and other parameters that we haven't considered yet. So it goes, we start with the ZR relationship because this is the simplest model, probabilistic model we can come up with. It's pretty easy. And then we enrich it by extracting as much information as we can from both the measurements but also the physical interpretation they have of it. For example, we have, okay, I can provide some, here is the conditional, so the black line is a current conditional bias you have on precipitation rate based on the parameter on the x-axis. So that's as a function of reflectivity. That's the black line. Pretty significant conditional bias. When you apply this approach, you can significantly reduce it. Okay, let me see. Here are the effect of the epsilon parameter. So epsilon in the algorithm, how it is formalized, is kind of it concentrates all the shortcomings of the hypotheses they are making in their physical interpretation. So this is a target of choice to try to improve the retrieval. So now, we are going to investigate step by step all these parameters, but also features on the profile that they may not be using. For example, the difference between the cutoff height and the freezing level is a quantity that we can easily compute and enable us to target, distinguish different macrophysics processes that are likely happening. So, yeah, work to be done.
Sorry, just let's move on. Okay. Engineering talks. You ready? Yeah. Okay. Our next talk is going to be remote. Sorry to cut short the conversation.
Good morning.
We've got.
I hope you are enjoying the conference. I wish I could be there with you, but I couldn't make it. Still, I would like to share some results of a study that we have performed recently. So let me start by sharing my slides with you. I hope you can see them. So the study is about the value of quantitative precipitation forecasting on stream flow forecasting, and the context is basin spatial scale. Doesn't matter and how. Well, first let me start by defining stream flow forecasting. So we know that river basins respond to rainfall forecasting with some delay. So that delay puts us into the future. So monitoring rainfall up to now, up to the current moment, the response will be in the future. However, I don't call this forecasting. For this process to be stream flow forecasting, the input, the driving, the forcing of the hydrologic model has to be also forecasted. So I will stay with this definition. And to get you into the mood of this problem, let's consider the following situation. Let's say that there's a forecasted rainfall. Let's say that there's true rainfall. So if you look at it from the meteorological point of view, well, this forecast is pretty good. So it has the right shape, pretty much the right magnitude. It is just displaced a little bit. Now, if you take a hydrologic, perspective and your interest in this basin, well, then this is a terrible, forecast. It is also a bad forecast for this basin, right? Because things will happen and we have no warning that they will happen. However, if you take a perspective of this basin, then this forecast is pretty good because both the forecasted and true rainfall are contained in the basin. And if you are standing at the outlet of the basin, you really cannot tell where the water is coming from as long as the two have similar travel time to the outlet. So based on this, we can see that flat forecasting still is scale dependent. And now, can we see this in actual data? So here we consider for the QPF, the HRRR, a high resolution rapid refresh product available for the last few years for the whole country. We analyzed 7 years of data. Every hour, the next 18 hours of rainfall are projected. For each hour, it is a national grid with 3 kilometer resolution. We analyze data at some 7,500, basins, and the radar-based MRMS product is used as reference. So the organization of some of my results will be according to the river basin centers here in the US, about 12 of them for CONUS, and also the locations of the stream gauges. Well, I will start with a very simple analysis. I call it rain to rain. So it will be comparison of HRRR to MRMS, again, radar-based product, as a function of forecast lead time. But first, just one image of the probability of detection of rain based on this reference, product. So we can see that in the West, it's not so good. So there are blockages, there are gaps. In the central US and the East, it's a little bit, better. So our reference is not that great, but this is the best we have. So now if we just calculate simple correlation coefficient over each basin, so now for each river forecast center, the basins range from just few square kilometers all the way to 100,000 square kilometers, and we can see that there is a strong scale dependence. The bigger the scale, the higher, the bigger the basin, the higher the correlation is. Now, this is just 1 hour ahead. If you now go 18 hours ahead, then the correlation drops, significantly, and for many the average type of basins, say 1,000 square kilometers, it's just about 0.5. So that's nothing, to write, home about. Well, if we now go to the second analysis, so this will be just do we have ability of detecting floods? We perform a categorical analysis, just detection, false detection, no detection. Here the threshold is mean annual peak flow from historical data at a given gauge, which is according to a hydrologic rule of thumb, a bankful flow. And so this way we can compare all the gauges by this uniform measure. Also, it is worth noting that the producers of the stream flow forecast, the National Weather Service, they don't publish data before data assimilation, stream flow data assimilation. So we call this at the USGS gauge, but we also analyze data at a river network link just above. So that doesn't have benefit from data at that gauge. It may have some benefit from an upstream gauge. So what do we get? So for probability of detection, we get this plot here as a function of lead time, and we can see that after about 6 hours or so, that probability of detection falls to about 0.5 or so. If we go above the gauge, so no benefit from data at the gauge, well, the situation is a little bit worse. Now, sometimes there is no gauge upstream, so there is no benefit from correcting the gauge upstream. And in this case, as you can suspect, the situation is worse. So there is a plot of a similar statistic, the true skill score. And here you can see that after some, let's call it 10 hours, basically there is no skill. There is no skill better than just a random guess. This at that gauge that receives benefit from the gauge upstream. If you consider the link of the above the gauge only, well, then the situation is not very good at all. Well, so there's a synthesis of all the data for 18 hours of lead time and across basin, scales. And if you closely track the data here, you will see that for the large basins, it really the skill doesn't matter. so there is very little, effect. But for small basins, the skill decreases, very quickly. So you can see like from here to here to here to there after 4 hours, very little, skill. If you go above the gauge, then the situation is much worse. As a summary, as a lesson from all this, I can say that it is the stream flow gauges that save the day. So that's all I wanted to share with you. This is a paper where we published all these results and much more, and hopefully we will follow up with additional results, additional analysis. Thank you very much.
Hello. Hello. Do we have any? No. Okay, he's on. Okay.
All right, last of this session, and then we'll have a really cool talk after that. All right, guys, I'm gonna kind of switch gears and talk about the communications side. But I do want to say I think this is very timely considering we had an amazing panel session and we've been having some amazing discussions about applications. So I want to kind of build on all that and talk about the application space. I am going to talk about it kind of through the lens of GPM and applications engagement, where I want to kind of highlight some lessons learned from doing how we solicit needs to get those lessons learned, and how that kind of helps us form, or I'm going to suggest a couple opportunities in the strategic communications space. Okay, I'm not going to dive into this too much, but just as a reminder, GPM considered applications way before launch and continues to consider applications post-launch. And what do we mean by that? We want to make sure that users are able to understand how to use the data, are using the data into their systems and processes for decision-making that directly benefits society. And we want to continue engagement to keep that going. But it doesn't just stop there. We do want to make sure that as we're engaging, we are systematically documenting these needs, data gaps, and opportunities through these engagement efforts. I'm going to actually go to the next slide just to save some time, so I'll talk about it here. So focusing on those two things of engagement to actually help people ingest GPM data into their systems, but also documenting needs, a big part of that is actually creating awareness and perception. So really going to the users and meeting them where they are at different levels, whether they're novice users of GPM data, satellite data, remote sensing data, precipitation, et cetera. And really creating an idea of the value of GPM data for them. And that helps get them to the knowledge gain of really understanding opportunities that maybe how precipitation data like GPM could come into their systems to support them going forward. And how do we do this? Well, we meet them where they are. Again, we want to foster connections by bringing scientists to them, by bringing communication folks to them, and really just setting the stage for conversation. But we also set up interviews, we attend meetings, conferences, we conduct analysis, and even go through publications to see what's kind of the latest research going on with respect to the application space. This is really helpful not only to increase uptake and use of GPM data, but it helps us, again, to define those data requirements and continue to understand those data requirements as we go forward, their needs, and data gaps. And I just want to give you an example is that one part where GPM is going into is really building into the NSF-funded industry-focused centers where industry is helping fund academia to do research. And we are having a front row seat to those to understand the insurance and finance sectors, really what are their needs and where are they going forward and how academia can play a role to help address those needs. Another one is just internally for the GPM mentorship program. Vasko and myself co-led a mentorship program to really bring experts to precipitation users throughout the globe. And that's really building relationships. And key to relationships, helps you, one, start the conversation and build trust across users. But another way to really help understand and get to documenting needs is really showing use cases and showing the success of GPM data. It helps us highlight the use of GPM data, how that data is being used to inform action, such as GPM into a hydrological model for flood estimation, to then how it benefits society. And so GPM now, especially across iMerge, we have over 100 plus, I mean, like not even users, but I'm saying case studies that we have documented. And these are just from, from the past year alone. Google Flood Hub is using our data, incorporating iMerge early specifically into their hydrological model to generate hourly forecasts to help not only governments, nonprofits, but to individuals throughout the world. Then we have the UN Food and Agriculture Organization that they're creating their own value-added products of 1 and 3 day accumulation estimates using iMerge late to really see the impacts of agriculture after extreme event. And again, that information is then going to humanitarian aid organizations to understand where to deliver aid or where is it needed most. And then speaking of insurance, just going back to that, we have a range of users across this, and Floodbase is kind of one of our newer users that are leveraging late and final products with inundation observations to really generate their near real-time flood maps. This helps trigger rapid parametric insurance payouts. I'm going through this quickly because I really want you to understand that through understanding developing use cases, we can document their needs going forward. And this is brings me into lessons learned. I think we already recognize global graded precipitation products are extremely popular and they're extremely successful across the application space. Why? They create a very accessible way to learn and how to use precipitation data for decision making. We also grew up with understanding weather maps, and I think it's really relatable to these folks that are using it. But also the timeliness of data. iMerge, again, as I said, applications was considered pre-launch. So really, the development of iMerge, having a 4-hour latency has been instrumental. I know folks want less than that, but 4 hours, they have said, many on the flood side said, this is adequate. Well, I'll take that. But it goes into even more defining these needs, these gaps in interest. As you'll see, I don't think these are really new of what we've talked about over these past few days. And I think that's really amazing that we have started to capture these needs. And I just want to break them down. This is not an exhaustive list, but even within the data access and usability, consistency across product versions. And this even goes with taking care of naming conventions. It can break code, so even having V7 versus V8, warning users how that impacts their systems and processes going forward. Even flexible extraction, more of, do we have tools to be able to do country scale data? So UNFA, or so Food and Ag org, was actually saying they need an easier way to do that. There are tools to do that, but are they using and are they aware of those? To accessible documentation, there are a number of users that we have too much jargon to them. They spend too much time trying to understand and translate what we provide in ATBDs. So how can we make an applications relevant documentation that they can look at of what these data products are? Again, snow and hail, as we go across the insurance sector, that's going to continue. Hail, especially across the southeast US, has been one, and in Argentina. Complex terrain, the interest there, because applications are across mountainous terrains, even coastal regions that packed maritime operations. Continuity, no surprise there. And then people always want the fastest data. So if we can have sub-hourly, people want, if they can have even less than 2 hours, that would be instrumental to them. We are seeing across this application space downscaling. People are application users themselves are actually looking and exploring ways to use AI to really look at downscale ways to address spatial scales that work for them. Again, uncertainty, going to that, that's no surprise, but even to extremes. How are they talking about that? How do they, how does what we deliver for extremes fitting their needs, data transparency, and even their interest in they're interested in exploring the AI, machine learning, for really looking at hazard prediction and downscaling. So we have users that are doing it themselves, but we are also having them wanting to ask the data developers, are they using the right techniques? Are they being careful of how they do it? So they really want to have this conversation. I kind of skimmed over all of this, and I'm already at 8 minutes, geez, but I just want to say, here's to set the stage. But this goes to here is where I think us having, as a whole, we've really captured a lot of, what these needs are. And I think we need to take a step back and say, this is a great start or even a journey as we go forward. However, this comes limitations. While we have all this information, just because we have this list doesn't mean if we check it off, we're addressing every need from every community, and because no one size fits all. These insights tend to be, as we engage users with the time that they have to engage or even their resources, they might actually have their answers rather vague to us, or information that we need more information from them. And so it doesn't really help us inform how we're going to use those actions into data product design, which creates these bottlenecks to really have actionable technical requirements that translates back to the data development. And so quickly, I just have some examples, such as we have people that say, we need earlier warnings and quick delivery, like the quickest delivery of data. But my question to them is, well, what's the threshold of being useful and not useful? Can you expand on that? If they need better extreme detection, do you want in percentiles, return periods, what confidence intervals, what areas and mindset are you thinking of? They might say, I just want good data. How do I know if it's good? Well, good to them is different and can be different from good to data to us. So this is really trying to understand both sides. And that brings me to really wrapping this up. I know I'm a little over, is just to say that, going forward for the application strategy is just something to suggest and kind of move forward of how can we work as a team, is that first recognize that when we do engagement, it might not naturally elicit technical specs, but that brings us opportunities to how can we have that happen. And I think one way to do that is we need to continue to engage application folks that really reach out to communities, need to continue to engage data developers and really hear from you, what are some possibilities of what we can do with the data to deliver that information? And also, what are your interests going forward with these folks? And that brings into really streamlining to like the right technical metrics that we can develop. So if we can bring out the possibilities from the data developer side, such as can we provide confidence intervals, quantile information, but this can really help us generate the limitations we have now to produce those, but even tell these folks as we go forward to build trust to saying, if you want that, that's gonna take the next 5 years, but that's something we'll have in the next generation. And so all of this is that I'm really proposing is we do need a framework to build the technical metrics of what's possible within our community. I think that helps then us build that language, because of a lot of it can be vague or misrepresented of what's uncertainty to them may not be what we're thinking here. So how can we actually build another framework of what users needs to translate back that to us to be more effective, reduce costs. So if we try to provide something and it doesn't work, that's cost and time. And it also helps us pipeline to be more effective in data product development. So again, I'll just end with this, is saying, I want to hear from you. I really do think us building a framework to establish technical metrics and what's possible across our space to be able to use that as a communication tool can help us bridge the gap, but also while primarily addressing the needs of users. And thank you. I know I'm a couple minutes over. I apologize. And then Vasko and I officially completed the ebook for GPM mentorship program. I just want to put a plug in here. It has over 50 case studies documenting the experts across GPM that volunteered their time to work with users to develop case studies and really highlight the capabilities of data. And I think one thing that's been instrumental is that it really has helped build the precipitation community across this space and form relationships that I think, really started here. And then we have an example, someone in this specific audience is already about to publish a publication with the user. And I think this just shows the success. And I'm sorry, I will stop there. Thank you.
That's great, Don. Any questions? Or do we want to? Okay.
Okay, so we're entering the final 30 minutes of IPC15, and we're going to do so with our last keynote talk, a shared keynote between Burke Griggs in person and Scott Eineck. Shall we start with the PowerPoint or? Okay. Awesome. How do I advance this slide? Here. Okay. All right. Okay. Thank you, and I know that I'm the last one here. I appreciate the courtesy. More importantly, I appreciate the invitation to be part of this august group. What I'm going to do partially builds on what Andrea talked about, selling this group on the legal and policy potentials of the work that you do. So I have a fairly simple argument here. I don't think it can be refuted. Again, American water law, natural resources law is littered with terrible ideas and terrible principles that we have gradually overcome. And I think that the basic argument today that I'd like to give today is we have a number of water emergencies in the United States. I'll just focus on two, and how precipitation science can potentially assist in reducing some of the harder edges of those emergencies, and more importantly, assisting with better water management across boundaries, water management regimes, but also when we think about property rights and the use of water, precipitation science can help us improve how we articulate those rights. So, this is the first emergency. The New York Times had an article on it yesterday. Anticipate more articles. This is the most important river basin in the United States. 40 million people depend upon it. It has a $1 trillion economy. It is also probably the legally most complicated thing in the United States. I've listed just, back of the envelope, the laws that apply to this basin at the international level, the national, regional level, the federal level. There are 29 recognized indigenous tribes in the basin, and then the different state laws of 7 different states, which have different water laws. Some have different water laws for groundwater than they do for surface water, such as Arizona and California. So, these laws are established to build stability, to build predictability, and at the risk of being too much of a soothsayer, I think they will both fail. The Colorado Basin is going to come into legal failure in 2 different ways. And this is the basic reason. The graph on the left deals with snow cover. The largest reservoir of moisture and water in the Colorado River Basin is winter snowpack. And how that translates to the 2 largest artificial reservoirs in the United States, Lake Mead and Lake Powell in the lower Colorado River Basin. The graph on the right shows total reservoir storage since 2000. The perhaps more important line is the red line in the middle, which is the total storage of Lakes Mead and Powell. Those are legally important because that is, Lake Powell is where the upper basin states, Colorado, New Mexico, Utah, and Wyoming, have a legal requirement for a certain amount of water to get to that lake. And the deceptive part of this graph is we have a mega drought, the worst in the basin's history, that started around 2000. So you'll read stories about the Colorado River Basin that are saying snowpack is 25% of average. It's actually worse than that because our average is now a 30-year average, which takes into account mega drought numbers. So what are the sources of legal failure? The biggest one is we overestimated the amount of water in the basin. People have written books about this error. It is stuck and codified into the Colorado River Compact. And that is going to be very difficult to undo legally. The last thing I want is this Congress opening up this compact in this basin. There has to be a different way to deal with this fundamental error. Also, assumptions of stationarity, the future will not be like the past.
And the original compact, signed by these 7 states over 100 years ago, has intentional legal ambiguities. That's how parties negotiate a contract. We can't agree on something, let's use ambiguous language so that we can move forward and at least have something that's better than nothing. So these are chronic and often defensible reasons behind ambiguities in legal documents. Physical challenges, I don't need to burn your time on this. I've already mentioned them, except for the third bullet point there. It's a stationarity problem. Because snow is falling later in the year and rain is coming earlier in the year, flows from these reservoirs are no longer well-timed to when the major water users need them. And Western water managers have been dealing with this problem since the 1970s. Even though the governors who appointed them probably didn't want to admit this, Western water engineers have been at the forefront of global warming problems. And what you're getting is early releases of water from reservoirs that then flow down basin, cannot be captured for beneficial use, and thus qualify legally as a waste of water. And this is a chronic problem. So when will it fail? Part of it will fail this summer. The United States, under this administration, is issuing an environmental impact statement for the management of these reservoirs. Depending upon which states are burned by this plan, those states will likely sue. And they'll have good arguments because the way in which the United States has presented this EIS has been less than sterling. The second aspect is an interstate challenge. The lower basin states, Arizona and California, will likely sue the upper basin, Colorado, New Mexico, Utah, Wyoming, under the following ambiguous language: that the upper basin states will not cause the flow of the river to be depleted. On a 10-year average, rolling average, 75 million acre feet. What's the legal meaning of that term? This is where I want to burn a little time, not too much. This is about causation. One basin is going to be arguing causation. The upper basin will be arguing, we did not cause the water to be depleted. Climate change, soil desiccation, differences in the water cycle. That's what caused most of it. The lower basin will be de-emphasizing causation. They'll be saying, look, a number's a number, a deal's a deal. Where's our 75 million acre feet of water? And what is terrifying to me, and should be terrifying to any water lawyer, is we are going to let 9 Eastern United States lawyers decide this question. Just because they're on the Supreme Court of the United States does not make me feel any better about their ability to resolve this question. Okay? Science should be assisting in the legal interpretation of probably the most important sentence written in the Colorado River Compact. We know the law is failing because, first of all, it puts people in impossible choices. Under a 1968 law, Arizona gets water from the most expensive reclamation project in American history, the Central Arizona Project. The cost of getting that water is that Arizona subordinated its priority to irrigation districts in the Imperial Valley of California, where all of our lettuce comes from in the United States in the winter. So when the manure hits the ventilator later on this year, and we don't have 75 million acre feet, will a presidential appointee at the Bureau of Reclamation decide that lettuce growers, all 80,000 of them, should get their water before the city of Phoenix, which has 4 million people? We know what the decision will be. Phoenix will win. We also know that that decision will break federal law. Okay? This is the sort of system we're working in. It's going to lead to litigation. Litigation is usually characterized, not unfairly, as failure. It also creates a lot of short-term reactionary fixes. What the United States is trying to do is a series of 2-year fixes to a problem that has been 100 years in the making. And that is proof of legal failure. The second emergency, I'll go a little more quickly because my colleague Scott will discuss this. These images, courtesy of the European Space Agency. This is the Great Salt Lake on the left in 1988. Notice the island in the lower right-hand part, Antelope Island, is actually an island. On the right, 2022, it's a shadow of its former self. And the desiccation of this terminal lake, which is right on the western side of the Great Salt Lake City metroplex, is having very serious problems. The legal infirmities are similar. In the Colorado River Basin, we overestimated water supply. In the Great Salt Lake, there is a water right attached to the lake. We just don't have a number for it. Okay? I've been hearing uncertainty as a problem among this group. This is a bigger uncertainty, right? How much does the lake need? Sounds like a scientific problem. That science is not embedded in Utah state law. And if we have water to allocate to the lake, will we be taking water rights away from other users? There's a potential legal challenge there in Utah law. Same desiccation, mega drought problems, but also the same problems of over-appropriation. That's a term you'll hear in water law quite regularly. It's where there are more water rights than there is water to supply them. It's a chronic problem ever since Elwood Mead wrote about it about 130 years ago. We tend to grant more water rights than the basins can supply. So, here is a depressing picture of a depressing place, a dry Great Salt Lake, raising up all sorts of nasty, toxic dust. And a colleague of mine, long-term water lawyer in Salt Lake, he's a rancher, he's an ultramarathoner, he plays tennis. He now has emphysema. Never smoked a cigarette in his life. And he got emphysema from this dust. So it's a public health hazard of the first order in Utah. Where is this failing? The state of Utah knows what it needs to do, but it's not reallocating the water rights in a time of emergency. The state does not have the confidence to know and to act. The state doesn't have the confidence to act upon, to perform the actions that it knows it needs to do. This may change in the next year or two. But we've already spawned litigation and the same sort of instability that we see in the Colorado. So with that, I would like to turn it over to Scott.
I'm Scott Heaney, the USGS Utah Water Science Center. I'll pick up where Bert left off with the Great Salt Lake and discuss some issues that we commonly work on in closed basins, which represent unique situations for water budgeting, and the role that understanding precipitation, parts of the water budget, how that plays into some of the work we're pushing forward. One important thing to notice here in the Great Basin of the Western United States, there are a series of lakes in closed basins. So the only discharge from these important aquatic resources is discharged to the atmosphere by evaporation and transpiration. And then, of course, surface water and groundwater are critical inputs to these lakes, and precipitation. And changes in lake volume, which is something I'll talk about quite a bit, is really quite important. And in a situation like the Great Salt Lake, the surface area is so large that direct precipitation on the lake surface can account for a significant portion of the water budget. And in smaller lakes in particular, you can, I'll demonstrate that we can actually document volume changes in these lakes that are related to precipitation events. So, yes, the greatest uncertainty, these types of water budgets is precipitation to evaporation ratio. And here at Great Salt Lake, you're seeing a lake level record here. The bottom in red and in blue is a record coming out of the historic low of Great Salt Lake. And you'll see elevation peak on the y-axis. That this is common for Great Salt Lake to have the lake level fluctuate by a meter or two per year. And this relates to changes in volume. And these volume changes are really important for water budgets. And with the bathymetric mapping, which is essentially underwater topography, they can turn these lake levels into areas and volumes, which becomes really important. And then at some times of the year in these types of systems, you get a stable lake level, and in equals out. And what this means is we can measure in, we can know out. And that means if we can measure surface water and groundwater and precipitation inputs to the lake, then we can know the evaporation rate off of the lake. One of the critical items is debates over groundwater contributions to water budgets. We can measure surface water inputs to a lot of these systems quite well because it's obvious. Groundwater contributions are more cryptic. Now, if we can have accurate precipitation estimates, then by difference, we can understand groundwater contributions to them. And then I also want to point out that the short-term spikes you see in that lower lake level curve are typically related to wind at Great Salt Lake, but in other systems, we see those types of spikes or rapid step changes when you zoom in can be related to precipitation inputs. So in smaller systems, such as southeastern Oregon, I'm going to show some examples from there before we move down to central Nevada. Variations in lake level, lake area can be related to specific weather events, prefrontal winds or precipitation. And in these types of small, shallow lakes, there's some really interesting opportunities to understand precipitation and its importance in these systems, because a lot of these lakes are dry at some points in time. They completely desiccate. I'm showing you here an example from Lake Ebert in southeastern Oregon. On the left-hand side, you see LIDAR, airborne digital elevation data collected when the lake was completely dry. We can use this high precision data to then relate lake elevation or lake area to volumes, as you see on the right here. And in these episodically wet, dry lakes, I'm showing you some examples here where we relate elevation for the, some of these lakes in that region of southeastern Oregon to area or volume. And this is the standard approach to use surface elevation to estimate volume and volume changes. So, and typically in important systems, you have a 15-minute or more precise data for the elevation of the water surface, and then that can then be turned into volume changes or rates of volume change. But one of the opportunities that we have in these types of systems are dry lake beds that experience major precipitation events. In these scenarios, we can turn area into volume when we have this sort of high precision digital elevation data for dry lake beds. And when you have a dry lake bed and you flood it, you can very confidently map the newly wetted area. It's more complicated when you have a wet area shrinking, because wet mud can be difficult to distinguish from water in a lot of remotely sensed scenarios. I'll just show you an example here from Nevada. This is a place I've been working for 15 years almost, and closed basin very near an important lithium brine resource. And I've never, ever seen water here. And so in September of 23, there was major monsoonal precipitation in Southern California and a lot of central Nevada, putting huge amounts of precipitation on the landscape where typically you don't have it. Just showing you an example here on the far left, you see a lake with an island, that's Mono Lake, California. And on the right, in circles, what you're seeing is wetted areas that were dry the previous observation period. So this remotely sensed data now, combined with digital topography, allows us to estimate the volumes of water that fell on that landscape and accumulated in these lakes. And this can be important for a number of reasons. Ecological impacts are actually quite important to this water volume as well, and understanding this in terms of overall water budgets and how episodic events like this contribute to the water budget rather than long-term means are turning out to be really quite important as well. And then I want to just briefly turn to and share another example with you from the Central Andes, South America. Another place where there are closed basins, there's enormous ecological and mineral resource interests, and there's very sparse precipitation data. And precipitation data is really critical for a few reasons. It helps with the management of the resource, and you know, in these systems, we're using remote sensing to understand water budgets and really working on the evaporative discharge from these closed basins. That gives us a total water budget. But when we get into management scenarios and groundwater modeling scenarios, resource protection, other issues, regulation, understanding the spatial and temporal distribution of precipitation turns out to be really important as we create groundwater models. And those are the types of tools that are really going to be used for resource management. And in this case, accurate precipitation data is critical. A major breakthrough in the understanding of the topography and climate relations in the Andes came about in the early 2000s as a result of precipitation data from the tropical rainfall measuring mission, showing you here one of the classic publications which documented these relationships. What you see, however, though, is you can see it even at this scale, very coarse resolution, spatial resolution, and then, you know, everything has been to less than a half a meter per year of rainfall in that deep dark red and on the right hand side. And that is the place where we need actually better spatial, temporal resolution and better resolution of amounts of rainfall. And so these are target areas for greatly, you know, for improved precipitation data sets that will directly impact management of ecological systems and management of mineral resources. And one of the keys here with the types of precipitation data sets that are required, there are 2 key points. One is validation data is really important. Remotely sensed data is really the only useful way to attack something at this scale. But validation data are really limited. They're getting better now as more and more lithium brine operations come online and they're collecting data. And there's potential here to validate this and put this as inputs to groundwater models. Now, one of the keys here is the hydrogeology of the Central Andes is you know, understudied in many regards, and in particular, groundwater recharge rates. Turning a precipitation volume into a groundwater recharge volume is very complicated, and in the hydrogeology of the rock types up here, we believe that the recharge rates are abnormally high relative to arid regions around the world, and this is a place where better precipitation data would help lead to better hydrogeological tool for measuring, monitoring, managing. And I'll just conclude here with a kind of a digital image made from a few photographs by my friend and colleague Ron Larson for Lake Abert in southeastern Oregon. And just point out that in arid and hyper-arid environments where we really need to understand precipitation much better than we currently do, it's the spatial and the temporal variability that control everything. So in the places where we have the least amount of precipitation, we also have the greatest amount of heterogeneity both in space and in time, and these present major challenges with advancing precipitation science and its impact onto the management of resources.
Okay. He'd be here to answer questions, but he's probably still recovering from the Argentina-Algeria game, which he was able to attend in person. So, wrapping up, what can you guys do for us pathetic, badly planning lawyers and for the legal system as a whole? Obviously, water budgets are critical. The water budget is the beginning for so many water management and water rights decisions. It can also improve the way in which a basin within a state or a basin that is interstate fits between the legal allocations of water and the ways in which the water supplies in that basin are changing, whether it's reservoir management or whether it is the temporal and physical dynamics of the system. I can't advance, Bosco, sorry. I'm almost finished, I promise. Okay, all right. Still frozen. In the short to medium term, what the United States is doing right now, they need more of you, okay, in terms of forward-looking assessments of water availability. How badly will Powell and Meade be crashing over the next 2 or 3 years? That is a multi-billion-dollar question that we're facing, from the ski areas of Colorado down to the city of Los Angeles. And it can even affect how we interpret legal documents. I don't think it's too much of a push with this emphasis on causation to discuss and to analyze that. But in the long term, I'm so sorry. I got it, believe it or not. I did it all by myself. It can perform two really important things. More than any legal argument, it can discredit archaic assumptions about how the law works, about how legal allocations work. If a legal argument, if a contract, an interstate compact, is founded upon assumptions that we can demonstrate are now mistaken, then that provides a compelling legal argument to reform that document, okay? And science can do something here that I think the law on its own cannot. It can also help us build better water rights, describing the property interest in the use of water in such a way that it reflects the dynamics, the temporal, spatial, and quantitative dynamics of what people actually own when they have this property right to use water. If we don't make these rights more flexible, then their fixedness will become brittle and they'll break, and they're breaking across the West. And so with that, I think I can be somewhat optimistic. Can water law change? Can it accommodate? I believe it can. These are two famous quotes from two really old water cases, sort of Old Testament water law, that water law has to acknowledge conditions of aridity and topography, and also what we view as reasonable and beneficial changes over time. The 1935 case, irrigator argued that flooding his entire field 3 feet deep in the San Joaquin Valley of California to drown prairie dogs was a beneficial use of water. And the court said, as far back as 1935, that actually there are better ways of using water, or perhaps better ways of killing prairie dogs than using thousands of acre feet of water. Science can improve the law. I'm repeating myself. We don't need to detain ourselves on this slide other than the 2 boxes. Scientists can be incredibly useful in litigation for disabusing courts of such ridiculous legal arguments as an interstate compact between Nebraska and Kansas that allocates the waters of an interstate basin does not include groundwater. Because groundwater, the word groundwater does not exist in that compact. Nebraska made that argument, okay? And the judge, using experts, said to the extent groundwater pumping depletes stream flows, that water is in the compact. So that's very basic water science. Imagine what you guys are capable of with what you're doing. And again, speaking to issues of causation, long-term predictability, ranges of volumes rather than fixed volumes. So, the ball is in your court. Please think about this. Please don't be a stranger if you come up with ideas to share among yourselves. How can you apply science to the law to make these allocation agreements more flexible, to make better allocation decisions going forward? For example, in the Colorado River Basin, we are not going to rewrite the Colorado River Compact. What we're going to have to do is come up with some sort of agreement that is an effective substitute for that. And that's where you are going to play a very important role. Where and how do you intervene? At the agency level, at the planning level, at the private sector level? How do owners of large water rights use their water? How can they move those water rights around as necessary? And finally, culturally, how do we work within our political cultures, which are at a very strained point right now, to accept these improvements? And I think that's a lot of what we're talking about this week. So that's the presentation. Thank you very much. I'm happy to take questions afterwards so I don't detain any of you from lunch. Thank you.
Any questions?
Thanks, Burke. Great talk. Quick question for just, you know, we can have action at the agency level, but what about even deliverables? Are publications enough, or do we need to think kind of outside the box of we have not saying that's just it, but publications and then making specific deliverables out like to the higher agency level? So I'm just curious, like strategically, how can we make even impact across doing fantastic research and having that science and building that published information or sending out published information, but really be more effective on that side?
I would be the greatest Secretary of Interior in the history of the United States, and I would be in that position for 3 days before I was impeached, okay? There are a lot of things the United States could do a lot better. I'm not going to criticize the USGS. I'm a huge fan of the U.S. Geological Survey, but one of the problems is I think there is such a professional emphasis on we are not going to advocate for a particular position that maybe the guardrails are too narrow in a lot of agency publications. I would love to see a USGS report that says, you know, the death of stationarity in the Colorado River Basin. That is not a scientifically controversial argument to make, okay? And from a policy standpoint, it would get the attention of people who say we can't assume that it's 1922 again. So the level of scientific quality at the USGS is extraordinary. It can advocate for science a little better while advocating for better science, for better policy. okay? Like Lake Powell probably shouldn't exist, okay? We now have geologists who have named the geological formation of silt building up in Lake Powell as the Powell Formation, which I think is hilarious, right? They can't use that in USGS publications because it's viewed as too controversial. You know, God, Darwin, physics invented rivers to take mountains to the ocean. That's exactly what's happening at Lake Powell. And we're not going to describe this as a man-made situation that will affect the water management of the basin. So I think that's just USGS as an example. Uh-oh, we got a Colorado in here. He's going to have a legal opinion.
Who's all too familiar. But I think one of the points you make, and I think one of the points we need to be cognizant of as well, is that the water availability on the Colorado is not just precipitation, right? It's also evaporation.
Yeah, yeah.
And so it's this integration of more than one field that I think we all need to be aware of, and we need to sort of address that. We are very stovepipe too.
Yeah.
But this is more than preset.
Right. And one thing that we need to be talking more about in the basin and any basin in the world is conjunctive management. This is where you guys' work is incredibly important. When you have intense rainfalls, how can we capture that and store it underground where it doesn't evaporate? California is doing great work there. There is more groundwater storage capacity in the upper part of the basin than we realized even 10 years ago. So to what extent could upper basin states harvest extreme precipitation events and build underground storage that could be released into river systems in dry years?
Thank you so much. I would invite everyone to reach out to Burke for further questions. And thank you so much for your keynote, also to Scott Eineck for participating. And this concludes IPC15. It's the end. You can remove your badges. And thank you so much for being here. I think it was a great 3 days of discussion. And that's it. Thank you.